So now we are going to discuss one more important concept is called as the star connection. So I've already told you for high rating machines we are going to keep the armature winding on the stator and the field winding on the rotor. So this is basically on the stator we are going to keep this armature winding in a star connection fashion, and we will see what is the consequences we are going to get. So let me consider these are the three terminals R, Y and B. And this is the ERY is called as the line, or we can say the voltage which is induced across the R and Y, or simply it is called as the line voltage. And this is the EYB and this is the EBR. So ERY is the voltage across the R and Y terminals, and EYB is the voltage across the Y and B terminals, and EBR is the voltage across the B and R terminals. So these are the respective voltages. And we can say simply, so now we are going to analyze one important things here. Let me consider ER1 at an angle of 0 degree, and this is called as the EY1 at an angle of minus 120 degree, and EB1 is called as the at an angle of plus 120 degree. So if you see clearly, if you draw this phasor diagram, we are going to get in a clockwise direction, which is RYB. So RYB. So therefore, let me assume each have the same amount of induced voltage. Each have the same amount of induced voltage, which is equal to E1. So therefore, this is called as the fundamental component. So let me ask you, this is a one indicates it is a positive phase sequence. It is called as the positive phase sequence. One means basically it is nothing but it is a positive phase sequence. So I have already told you it's the fundamental component. Fundamental component is called as the positive phase sequence. It is a reference one. So this is called as the ER1, EY1 and EB1. So this is the EMF induced. The positive sequence voltages are going to induce in the R winding, Y winding and B winding. So now if I go for the third harmonic, then see there will be no even harmonics, only there will be odd harmonics. So if I go for third harmonic, ER3 at an angle of 0 degree, EY3 is nothing but 3 into, just go for this one, 3 times of minus 120 is nothing but minus 360 is again equal to 0 degree. So EY at an angle of 0 degree, and EB3 at an angle of 3 into plus 120 is nothing but plus 360 plus 360 is equal to 0 degree. So therefore you can see all these vectors are in the same direction. So therefore they are in the same direction. So let me assume these voltages have equal magnitude of E3. So these are called as the third harmonic. So there is no rotation, they are in the same direction. So therefore these are the third harmonic components. And similarly, if I go for the fifth harmonic component, ERY at an angle of 0 degree, because 5 into 0 is again 0 harmonic, 0, and EY5 is equal to 5 into minus 120, it is nothing but, if you do simplification, still you are going to get EY5 at an angle of plus 120, and if you go for the EB5 into 5 into plus 120 is again minus 120. So if you draw the phasor diagram, we are going to get in the clockwise direction, in the anti-clockwise direction we are going to get RYB. So in the anti-clockwise we are going to get RYB. So we can say clearly it is opposite to the phase of the fundamental. So we can say this is said to be negative sequence. So it is said to be negative sequence, and this is the fifth harmonic voltages. So therefore ER1, EY1, EB1, ER3, EY3, EB3, and ER5, EY5 and EB5. So this is the fundamental component, this is the third harmonic component, and this is the fifth harmonic component. And the fundamental component, if I take this as the positive sequence, and ER3 is nothing but these are the third harmonic component, and ER5 is nothing but these are the fifth harmonic component. These are the fifth harmonic component are always negative sequence components. Then I can say that this is said to be positive sequence because I have taken the fundamental as a positive phase sequence, and this is the third harmonic component is also called as zero sequence, and these are called as fifth harmonic basically negative sequence components, because in the anti-clockwise they have the phase sequence of RYB. So it is opposite to the positive phase sequence. In the clockwise it is RYB, in the anti-clockwise it is RYB. So therefore for 60 degree phase split, suppose if you go for the 60 degree phase split, 60 degrees means I have already told you, for 60 degrees we are going to wound as one phase. For one phase in the one pole we are going to use 60 degrees. So 60 degrees is used for one phase itself only under one pole. So it is 60 degree phase split. Then what is the EMF induced per phase? EMF induced per phase is equal to under root over E1 square plus E3 square plus E5 square. Then line voltage is equal to root 3 times the phase voltage. So root 3 times of under root over E1 square plus E5 square. So therefore simply we can say that in the line voltage there will be no third harmonic components, only fundamental and fifth harmonics are going to present, but not the third harmonic component. So this is a very important point that you always have to do remember this case. So we can simply say that in the phase voltage we have third harmonic component, but in the line voltage there will be no third harmonic component. So therefore we can say E phase is equal to root over E1 square plus E3 square plus E5 square, whereas EL is equal to root 3 times of root over E1 square plus E5 square, because in the line voltage there will be no third harmonic components. Now if you go for the 120 degree phase shift, so 120 degree phase spread, then E phase is equal to root over E1 square plus E5 square, so there will be no third harmonic component, and EL is equal to root 3 times the this phase voltage, which is root over E1 square plus E5 square. So these are the important formulas that you need to remember for 60 degrees phase spread and the 100 degree phase spread, the phase voltage and the line voltage expression. So here the phase voltage is equal to root over E1 square plus E3 square plus E5 square, and the line voltage is root 3 times the phase voltage. Here you have to remove the third harmonic component. So you are going to get in this manner. Again E phase is equal to root over, for 100 degree phase spread you have to remove the third harmonic component, which is E1 square plus E5 square, and EL is equal to root 3 times the phase voltage. Just take blindly root 3 times the phase voltage, you are going to get in this format. So therefore we can say clearly this is a 60 degree phase spread and this is for the 100 degree phase spread. So these are the important formulas that you always have to remember. In a 60 degree phase spread, for line voltage there will be never third harmonic component, whereas for 100 degree phase spread, the phase voltage and line voltage will never have the third harmonic components. So for a 60 degree phase spread, the line voltage will never have the third harmonic component, and similarly for 100 degree phase spread, there will be no third harmonic component in the phase voltage and line voltage. So in a star connected system with respect to line voltage, third harmonic component is eliminated for both 60 degree phase spread and 100 degree phase spread. So you can see clearly for 60 degree phase spread and for 100 degree phase spread in the line voltage, there is no third harmonic component. There is no third harmonic component. You can see clearly here for the 60 degree phase spread and 100 degree phase spread, for line voltage there is no third harmonic component. So in a star connected system with respect to line voltage, the third harmonic component is absent for both 60 degree phase spread and also for the 120 degree phase spread. This is a very important point, which is, see, no matter whether it is a 60 degree phase spread or 120 degree phase spread, third harmonic component is absent for both the line voltages. It's a very important point. So the star connected system with respect to line voltages, the third harmonic component is eliminated for both 60 degree phase spread and 120 degree phase spread. Suppose if I go for the delta connection, suppose if the rotor winding on the stator, so because you are going to keep the rotor winding on the stator, if it is connected in delta, then what is the voltages which are going to get induced? I have already told you these are the three windings connected in the delta fashion, which is ER1, EY1, EB1, ER3, EY3, EB3, ER5, EY5 and EB5. So these are the things that we are going to get. So this is the R terminal, Y terminal and B terminal. Then let me assume the impedance of the coil. The impedance of the coil is equal to ZS is equal to RA plus JXS. As the resistance of the coil is very less, so we are going to neglect it. So it is nearly equal to J times the XS. RA is called as the resistance of the coil and XS is called the reactance of the coil. As the resistance of the coil is very less, so we are going to neglect it. So therefore it is nearly equal to J times of XS. So now I want to see what is the nature of the voltages. So if you see clearly, ER1 at an angle of 0 degree plus EY1 at an angle of minus 120 degree plus EB1 at an angle of plus 120 degree. Because I have already assumed ER1 is equal to EY1 is equal to EB1 is equal to E1. Then if this is called as the basically it's a vector addition of all these vectors. These are the balanced vectors with equal magnitude and a phase difference of 120. So the vector sum will be always equal to 0. So therefore we can say that the vector sum of equal balanced vectors when they have phase difference of 120, their summation is always equal to 0. Whereas if you go for the third harmonic component, I have already told you ER3 at an angle of 0 degree, EY3 at an angle of 0 degree plus EB3 at an angle of 0 degree, it is equal to 3 into E3 because third harmonic components are in the same direction. So therefore their summation will never be equal to 0. It is equal to 3 times the E3 because ER3 is equal to EY3 is equal to EB3 is equal to E3 that we have already assumed. So its value is equal to E3. So therefore 3 into E3. So it is responsible for circulating currents. If you do the addition of the voltages of the fundamental and the third harmonic and the fifth harmonic. The fundamental summation of the voltages is equal to 0 and the fifth harmonic voltages summation is also equal to 0, but the third harmonic summation of voltages will never be equal to 0 because these are the zero sequence components. So therefore we can say that the overall voltage is going to be present in the circular fashion. So therefore a circulating current is going to get flow because the overall net voltage in a circular is not equal to 0. If it is equal to 0 means the currents produced because of those voltages will be 0. So current produced by fundamental component and the fifth harmonic component in the circular fashion is 0, but the third harmonic components are going to produce the current because the summation of the voltages in the circle is not equal to 0. So therefore these are going to produce some amount of circulating currents in these windings. So third harmonic components are the responsible for producing the circulating currents. It's a very important point here. Similarly, fifth, the fundamental component and the fifth harmonic component. So fundamental is the positive phase sequence and the fifth is the negative sequence. So these two voltages, the summation of voltages will never give a resultant voltage. The resultant voltage is always equal to 0. So currents because of these voltages are always equal to 0. But ER3, EY3 and EB3, the summation is not equal to 0. So they are going to produce some circulating currents always. So I have already told you for some, if I go for the fifth harmonic analysis, same thing, ER5 at an angle of 0 degree plus EY5 at an angle of plus 120 and EB5 at an angle of minus 120 is always equal to 0. So therefore, first component and the fifth harmonic component will never give you any resultant voltage in a circular fashion, whereas only the third harmonic is going to give you a resultant voltage. So because of that, it is responsible for the circulating currents. Then what is the circulating currents? Circulating currents is equal to, see, the overall induced voltage is 3 into E3. So 3 into E3 by, see, in the summation there are 3 reactants. So each has a reactance of X3. So there are 3 reactants. So 3 into X3. So therefore E3 by X3. So it is a X3 is the called as reactance because of the third harmonic component. So therefore if X1 is equal to 2 pi FL, then what is X3? Frequency is increased 3 times. So therefore 2 pi into 3F into L, which is 3 times of X1. So therefore E3 by 3 into X1, where X1 is the reactance because of the fundamental component. So 3 times of X1 is the overall reactance because of the third harmonic component. So therefore we can say that 3 times of E3 by 3 times of X3, 3 cancels, we are going to get E3 by X3. E3 by X3 is nothing but 3 times of X1 because X1 is equal to 2 pi FL. So X3 is equal to 2 pi into 3F into L, which is 3 times of XL, because for fundamental frequency, then we are going to get a reactance of X1. For third harmonic, the reactance is 3 times of X1. It's a very important point here. So now we will see what is the, for 60 degree phase split and for 120 degree phase split, what is the EMF induced. See, in a delta connection, the line voltage is always equal to phase voltage. So therefore, always the line voltage is equal to phase voltage in a delta connection, irrespective of the 60 degree phase split or the 120 degree phase split, and its equation is always equal to same, which is equal to under 2 over E1 square plus E1 square. It is a free from third harmonic component. So irrespective whether it is a 60 degree phase split or the 120 degree phase split, the line voltage is always equal to phase voltage is equal to under 2 over E1 square plus E1 square. You can see clearly here third harmonic component is absent. So now let me see the triplet harmonics. So each triplet harmonic is called as zero sequence components. Now we will see what is the overall circulating current because of each and every triplet harmonics. So triplet odd harmonics, you have to consider only triplet odd harmonics, which is 3, 9, 15, 21 like that. So IC is the summation. So the overall circulating current is the summation of currents because of individual triplet odd harmonics. So for third harmonic, we have got the expression which is E3 by 3 times of X1. For nth one, for ninth one, we are going to get E9 by, which is 9 into X1, which is 9 into X1. And for E15, which is E15 by 15 into X1. And for E21, which is E21 by 21 into X1. Because X1 is the reactance because of the fundamental component frequency, and 21 into X1 is the net reactance because of the overall 21 frequency, which is this harmonic frequency. So for third harmonic, the circulating current is E3 by 3x1. We have seen all this one. For ninth harmonic, E9 by 9 times of x1. For E15, which is E15 by 15 times of x1. And for E21, which is E21 by 21 x1, like this. So if you add all these components, we are going to get the overall circulating current because of all the triplet odd harmonics. Third harmonic component provided it's a total effect inside the loop, so it won't come outside. So this triplet these the tribulin odd harmonics are going to show their effect only in the inside the loop but not the outside. So they are going to absorb in the outside region. So therefore in the line voltage they are not going to present. So all the third harmonic components are going to show their effect only in the circular fashion, only in the inner loop, delta loop, but not the outside. So they are absent on the line voltages. So this is a very important point. You can see clearly here. All the tribulin odd harmonics are going to provide they are going to show their total effect only inside the loop, so it won't come outside the loop. Now we will discuss some of the advantages of star connection compared to delta connection. So what are some of the important advantages of using the star connection compared to delta connection? Less number of turns per phase is required for same line voltage. See, the star connection for a same line voltage, we require less number of turns per phase. So in a star connection for same amount of line voltage, we require less number of turns per phase in star connection when compared to a delta connection, and less insulating material is required because they have less number of turns means the insulating them is also very less. So less number of insulation is required. So less insulating material is required, and due to the absence of circulating currents, resistive losses are less. So temperature rise is also less. So in a star connection there will be no circulating currents. So due to the absence of circulating currents, resistive losses are less. So because of the circulating currents, some losses will be there. But if circulating currents are itself is equal to 0, so there will be no resistive losses in the windings. So temperature rise is also very less. And the neutral point connection is available. So in a delta there will be no neutral point. But in this star connection, neutral point is available. So with respect to line voltage, third harmonic component is eliminated. So I have already told you in the star connection, irrespective whether it is a 60 degree phase spread or whether it is a 120 degree phase spread, in the line voltage you will never see a third harmonic component. So with respect to line voltage, whether it is a 60 degree phase spread or whether it is a 120 degree phase spread, in the line voltage we will never have the third harmonic component. This I have already told in the previous one itself. So therefore we can say these are some of the important advantages of the star connection when compared to delta connection, which is in the star connection for the same amount of line voltage we need less number of turns per phase. As the turns itself are very less, the amount of insulation which is material required is also very less, and in a star connection there will be no circulating currents. If there are no circulating currents means there are no resistive losses in the turns of the winding. So therefore the temperature rise is also very less. In the star connection the neutral point is always available, and I have already told you with respect to line voltage in the star connection the third harmonic component is always absent irrespective whether it is a 60 degree phase spread or whether it is a 20 degree phase spread. So now we are going to discuss one very important concept which is called as the effect of the harmonics on the induced voltage in alternator. So what is the effect of the harmonics on the induced voltage in alternator? So therefore we will see what is the effects of harmonics on the induced voltage in alternator. Suppose I have already told you the RMS value of the induced voltage per phase. If it is a fundamental harmonic, or we can say fundamental component is also called as the first harmonic, then the expression is equal to 4.44 phi1 into F into T into Kw1, where Kw is called as this formula we have already learned about the general expression. So for the fundamental component or the first harmonic means just keep here phi1 and Kw1. So this is the thing that you always have to remember. The remaining things are same, which is 4.44 F and T are same. Only this, see, F is also going to change for fundamental and the harmonic. But the remaining things 4.44 and the T are constant for each and every case. But the phi and the frequency and the Kw are going to get changed for the respective harmonics. Suppose if I want to find what is the RMS value of the induced voltage per phase because of the third harmonic is equal to 4.44 into phi 3 into 3 times of F into T into Kw3. This is the expression for the third harmonic component. In general, for the nth harmonic, the general expression of the EMF induced per phase because of nth harmonic component is 4.44 into phi n into n times of F into T into Kwn, where T is called as the turns per phase. So this is the expression that you always have to remember. The amount of EMF, the RMS value of the induced EMF per phase because of the nth harmonic component is equal to 4.44 into phi n into NF into T into kWn. The only the things that we need to vary is phi and frequency and the kW. These are the only three parameters are going to change for respect to harmonics. So therefore now if I want to do the ratio of the nth harmonic RMS value of the phase voltage to the fundamental RMS value of the phase voltage, if I do the ratio of this value and this equation, 4.44 are going to get cancelled, T are going to get cancelled, F are also going to get cancelled. Then finally we are going to get, which is kWn by kW1 into n into phi n by phi 1. So this is the ratio that we are going to get. If you do the ratio of the RMS value of the nth harmonic per phase voltage, that we have got this expression. RMS value of the phase voltage, the RMS value of the phase voltage because of nth harmonic to the RMS value of the phase voltage because of the fundamental component is equal to kWn by kW1 into n times of phi n by phi 1. So this is the value that we are going to get. Now this ratio n into phi n by phi 1, it is nothing but it is called as the ratio of the Bmn by Bm1. Now we will see why this equation is going to come. So from this equation we have got this expression, and now we derive the ratio of this is equal to this ratio. How we got this ratio, that I am going to explain now in a very detailed manner. So therefore this ratio, the ratio of this one is equal to this ratio. We will see why it is the possible case. So now let me tell you in detail the concept regarding this proof one, which is, suppose let me take a pole. A pole has a length of L. So this length is L. It's basically a pole. Here there is a rotor. So rotor is rotating under the pole. The rotor diameter is D and the pole length is L. And the waveform of the fundamental component of the magnetic flux density in this manner, which is a peak value of Bm1. So peak value of positive peak of Bm1 and negative peak of minus Bm1. It is for the fundamental component. It is the fundamental component. I have already told you the EMF equation of a transformer EMF, which is EMF induced in the transformer is 4.44 into 5m into Fn. It's a very important formula that I have already told you in the transformer classes itself, which is E is equal to 4.44 into 5m into F into N, where 5m is called as the maximum flux in the transformer, whereas in the rotating machines I have already told you the general expression, which is the RMS value of the EMF induced per phase is equal to 4.44 into F into phi into F into T into kW, which is called as the Kb into Kd. So this phi is called as the average flux. Here we have to use the average flux, whereas here we have to use the maximum flux. Here it is basically average flux. It is called as the average flux, or simply we can say average flux for pole. See, phi is called as the flux per pole, or simply it is also called as the average flux per pole. It is called as the average flux per pole. This is the case for the rotating machines. So now we will try to figure out the average value of this one. So therefore, the average value of the fundamental component is equal to the average value of the magnetic, the average value of the magnetic flux density of the fundamental waveform is equal to flux per area, which is phi 1 by A. So phi 1 is the fundamental component, so phi 1 by A. So phi 1 is equal to average value into M is called as the average flux. So phi 1 is called as the basically average flux. So therefore here is a constant. So therefore the average value of the fundamental component is equal to the average value of the flux per area. So therefore phi 1 is called as the average value of flux is equal to B average 1 into A. B average 1 is called as the fundamental component of the average value of the magnetic flux density into area. Then what is a B average 1? It is a pure sinusoidal. So 2 into peak value by pi, which is 2 into Bm1 by pi. And area is equal to, so area is equal to, simply area is equal to pi d L by P. So pi d L by P, or simply we can say this much amount of area which is covered by the pole of the rotor. So A is called as the area under the each pole is covered under the rotor. So we can say this much amount of area is being covered by the pole of the rotor, where L is called as the length of the pole and D is called as the diameter of the rotor. So we can say this much amount of length of the rotor is being covered by the pole, or simply we can say this much amount of length or this much amount of area is being covered by the rotor under the pole. See now here this is called as diameter D. So diameter D. So therefore what is the overall area? Overall area is equal to, see the circumference area. Suppose the rotor has a length of L, because L is nothing but if this is length, then the area which is covered by the pole and this rotor is also having the rotor length is also L. So this area is 2 pi r. 2 pi r is nothing but pi d. So pi d into this length is L. So pi d L. This is a total surface area of the diameter. It is a total surface area of the rotor. But we have to find only that area which is covered under pole. So therefore divide by P. So therefore we can say this much amount of area which is being covered by the pole of the rotor under one pole. Or simply we can say area under each pole. Or simply we can say in other words, this much amount of area is being covered by the pole under one pole of this rotor, which is pi dl by P. So pi dl is called as the overall surface area of this rotor. But we want only the area per one pole, so divided by P. So this is the overall area which is under each pole of the rotor. So therefore A is called as the area under each pole. This much amount of area of the rotor which is under each pole, or simply we can say A is called as this much amount of area of the rotor which is under each pole, which is pi dl by P. So therefore now what we are going to do basically, what is the value of phi1? Average flux is equal to B average 1 into area. B average value we know, which is 2 bm1 by pi into the area is nothing but this is equal to this value, which is pi d into L by P. So therefore now if we do simplification, pi cancels, and then we are going to get bm1 into 2dl by P. This is for the fundamental. So this is called as the phi1. So phi1 is called as the average flux for the fundamental. The expression is bm1 into 2dl by P. So I hope you have understood this concept. So this is called as a phi1. But for what is the for phi n? Phi n is nothing but here the peak value of the magnetic flux density of the nth harmonic component is bm1 into 2dl by T. Just you have to replace P by np. So therefore we have to replace P by np. Then we are going to get like this. Now if you do the ratio of the phi n by n into phi n by phi1, then we are going to get bmn by bm1. So bmn is called as the peak value of the magnetic flux density for the nth harmonic component, and bm1 is called as the magnetic flux maximum value of the magnetic flux density because of the fundamental component. This is for the nth harmonic component and this is for the fundamental component. Let me give you the concept again clear so therefore you can easily understand. That is the meaning. So n into phi n by phi1 we have replaced by bmn by bm1. If you do the ratio of these two things, we are going to get n into phi n by phi1 is nothing but bmn by bm1. So this is the thing that you need to understand from this concept. Here the phi1 is called as the average flux. It is the average flux, not the maximum value. It is the average flux. So this is the pole. Pole has a length of L. This is a rotor. This is from the front view, but from the side view there is also length L here. So therefore simply we can say that now here this is the for a fundamental component, the amount of magnetic flux density has a peak value of bm1 and the average value of the EMF induced in a transformer. The equation is 4.44 into phi m into f into n, where phi m is called the maximum flux. Whereas in the rotating machine, the average value of the RMS value of the EMF induced in the one phase is 4.44 into phi into f into t into kp into kd. Here phi is called as the average flux for pole, the average flux for one pole. So therefore now here what is the average value of this one? The average value of this one is nothing but 2 into bm1 by pi. The average value of this fundamental component, B average value is equal to 2 into bm1 by pi. Magnetic flux density is equal to flux per area. So therefore the average value of magnetic flux density is equal to average value of the flux per area. But I want the fundamental, so I keep the 1 here. So phi1 is equal to average flux of the fundamental is equal to B average value into area. Area is nothing but the amount of area of the rotor which is under the one pole, which is pi d into L by P. Pi d into L by P, because pi d into L is called as the overall surface area of the rotor, but I want only that area which is under one pole, which is pi d L by P. So A is equal to pi d L by P. So therefore we can say J is called as the area of the rotor which is under one pole. L is called as the length of the pole and B is called as the diameter of the rotor. So now we know B average 1 and A also. Substitute here, we are going to get phi1 is equal to 2dm1 by pi into pi dl by p. So pi cancels, we are going to get dm1 into 2dl by p. It is for the fundamental component. So what we have to do, this is for the fundamental component. If I want for the nth harmonic component, we have to go for the peak value of the magnetic flux density of the nth harmonic component, and we have to replace p by np. So if you do the ratio of this n into phi n by phi 1, we are going to get, which is simply bmn by bm1. So now we can say clearly that n into phi n by phi 1 is nothing but bmn by bm1. So bmn is called as the maximum value of the nth harmonic component of the magnetic flux density, and bm1 is called as the maximum value of the magnetic flux density of the fundamental component. So this is the thing that you have to always remember. So I have already showed the proof of this equation. So n into phi n by phi 1 is nothing but bmn by bm1. I have already shown the proof also. So therefore we can say that the RMS value of the phase voltage because of nth harmonic by the RMS value of the phase voltage because of the fundamental component is equal to the, we can say, winding factor because of nth harmonic by winding factor because of the first harmonic into here the magnetic flux density, the maximum value of the magnetic flux density because of nth harmonic by the maximum value of the magnetic flux density because of the fundamental component. So this is a very important formula that you should always remember. Now we will discuss about the silent pole alternator. Silent pole alternator means here the rotor will be in this shape. The rotor will have some spikes of poles. It is going to have some spikes of poles. If this is the shape of the rotor, it is called as a silent pole alternator. If this is the shape of the rotor, it is called as a silent pole alternator, because you can see the rotor has a spikes of some like this. It is called as the poles. It has a spikes of poles. It is called as the silent pole alternator. And let me consider the field winding. So field winding I am going to note in this manner. So you can see clearly I have taken this wire from here and again I have kept here again I have take it to here, again I have take it to here, and finally I have take it to the supply. So this is the winding I have done for all these things. So therefore here I am going to get north pole, here I am going to get south pole, here I am going to get north pole, here I am going to get south pole. See, this is the type of winding that you should do in order to get this type of poles: north pole, south pole, north pole, and south pole. And finally you are going to give a supply for this rotor. So therefore now here there will be small amount of holes. You have to keep this there are small amount of holes, you can see clearly here. Again, these holes, from these holes you have to keep some extra winding. It is called as the damping winding. So damping winding is used in the alternators for basically removing the hunting process. So therefore damping winding is used in the alternator to remove the hunting process. So therefore I will explain why it is specifically used in the coming classes, but up to now just remember damping winding is used for removing the hunting things. So therefore this is a field winding. On the top of it we are going to keep an extra winding. From all these poles we are going to connect all these poles in a circular fashion. This is called as the damping winding. So this field winding is basically concentric winding. You can see clearly this field winding, it is basically concentric in nature. So therefore it is called as the concentric winding, and this is the damper winding. So now this is the rotor part, but if you want to see the stator part, it is a circular fashion. And these are the slots. These are the slots in which we can keep the armature winding to get back the current. So with the help of shaft we are going to rotate this rotor. So therefore we are going to rotate this rotor with the speed of nr is equal to ns, and the EMF is going to get produced in the stator coils, because the armature coils are basically kept in stator. So whenever the flux is going to cut these armature conductors, then definitely current is going to get induced in them. So we are going to collect this current with the help of extra windings. We are going to take the terminals outside to collect the current. So therefore this is called the rotor diagram, and this is the stator diagram. In the stator we are going to keep the armature conductors to collect the current. You can see clearly, due to projected poles, it is having larger diameter and short axial length. See, in this rotor you can see clearly it has a huge amount of poles. It's called the projected poles. So therefore we can say it is having the large diameter and short axial length. So therefore the rotor has the huge amount of diameter but a short amount of axial length, means inside the depthness is very less. The depthness of this rotor is very less, but the diameter is very high. So you can see clearly from this projected poles, you can see clearly the diameter of the rotor is very higher, but the short axial length, the inside depthness is very less. Due to large diameter of the rotor, stator diameter is also very large. See, the rotor diameter is very high means the stator diameter is also very high, because more is the diameter of the rotor, more is the diameter of the stator. Both are same process. So therefore, due to large diameter of the rotor, the stator diameter is also very large. So more number of slots can be provided. See, as the stator diameter is very higher, so we can provide more number of slots can be provided on the stator. So very important point. So therefore, power is directly proportional to diameter square into the length L, the short axial length, where D is the diameter of the rotor and L is the short axial length of this rotor. So therefore, here I have already told you D is always greater than L. So D is always greater than L. If you do the ratio of L by D, because D is always greater than L, it is nearly equal to 1 by 5, or simply we can say diameter is 5 times the diameter is nearly equal to 5 times the short axial length. So diameter is always nearly equal to 5 times the short axial length, and the power output is directly proportional to square of the diameter and length of the short axial length. If these are high, then power is also very higher. So therefore, we can say simply due to the projected poles of the rotor, we can say that it is having the large amount of diameter of the rotor but a short amount of axial length, and due to the large amount of the rotor diameter, definitely the stator should also have the large amount of diameter. If the stator has large amount of diameters, we can provide large number of slots on the stator. So we can provide large number of slots on the stator. So if there are more slots, more amount of coil we can keep. So power is also very higher. So output power we can take is very higher, which is power is always directly proportional to square of the diameter of the rotor into short axial length of this rotor, and the diameter of the rotor is nearly equal to 5 times the short axial length of this rotor. It's a very important point that you always have to understand this concept. To obtain electromagnetics, concentric winding is provided in the non-uniform air gap length is present between the stator and the rotor. Due to large diameter, it cannot be operated at high speed. To obtain rated frequency, more number of poles are provided. Let me explain this one. To obtain electromagnets, concentric winding is used. So therefore, see, I have already told you on the later we are going to provide the concentric winding. So the concentric winding is used on the rotor poles to provide the poles, because the concentric winding is used on this rotor to provide the poles. So therefore, to provide the electromagnetics on the poles, concentric winding is used on the rotor, and non-uniform air gap length is present between the stator and the rotor. So you can see clearly a non-uniform length is provided between the rotor and the stator. Suppose if you see clearly, this is the stator. So if you take a circular fashion like the stator, so between the stator and this pole, the length is very less. But here, between the stator and here, the length is very high. So here the length is very less, but here the length is very high. So you can see a non-uniform air gap is present between the stator and the rotor. From here, the length is very less, but here the length is very high. So we can see a non-uniform air gap is present between the stator and the rotor. A non-uniform air gap is present between the stator and the rotor. So due to large diameter, it cannot be operated at high speed. See, as the diameter is very high, so you cannot rotate with very high speed. So we cannot rotate with very high speed, because as the diameter is very higher, so you can't rotate it very fast. The speed is very limited. You cannot operate more than a certain limit. So speed is limited here. So therefore, the speed of operation of the rotor, the moving of the rotor shaft is the limited speed. You cannot operate more than a particular speed. So therefore, it cannot be operated at very higher speed. So to obtain the rated frequency, more number of poles are required. So because here N is equal to NR is equal to 120 by P. If we do the manipulation, we are going to get F is equal to P into NR or NS by 120. See, I have already told you, if you want the rated frequency, constant frequency, then definitely the number of the rotor speed is very less. It means that you need to increase the number of poles. Then only you can get a constant frequency, because N is always lesser. So you have to increase the number of poles to get a constant frequency or rated frequency. So therefore, as N increases, F increases. As N decreases, F decreases. So because they are directly proportional, as N decreases, F decreases. But I want constant rated frequency, so definitely I have to increase the number of poles to make the frequency as constant. So to make the frequency as 50 Hz, increase the number of poles. Increase the number of poles. Example is the number of poles, the small example, the number of poles which are present here is nearly 12, 24, 26 in this fashion. So this number of poles are being present, which is like 12, 24, 26. Then the minimum value is 12. In this 7-pole alternator, the minimum number of poles required is 12 and maximum it can be anything. So minimum value is 12. So you cannot see less than 12. You can always see at the 7-pole alternator with a minimum poles of 12, but not less than that. So finally I can say that in a 7-pole alternator, I can simply say that it has a projected poles on the rotor. So its diameter is very larger, but the less short axial length. So because the rotor diameter is very higher, similarly the stator diameter is also very large. So therefore, as the stator diameter is very large, so we can include more number of slots on the stator. And I already told you the diameter of the rotor is nearly equal to 5 times the short axial length. As the rotor diameter is very higher and the stator diameter is very higher, slots are very higher on the stator. So therefore, more coils we can keep. So therefore, more output we can get. So power is directly proportional to d square into L, where d is called as diameter of the rotor and L is called as short axial length of this rotor. So if you want to provide the electromagnets on the rotor, we have to use the concentric winding. And also I already told you there is a non-uniform air gap between the stator and the rotor. And also due to the large amount of rotor diameter, it cannot be operated at a very high speed. So speed should be some it is less than a maximum value. So therefore, if you want to give a rated frequency, then definitely you have to increase the number of poles, because here NR is equal to NS is equal to 120 F by P. If you do the manipulation, we are going to get F is equal to P into N by 120. Yeah, because I used the notation N is equal to NR is equal to NS. So if N decreases, F decreases. So I want to make the frequency constant, so I have to increase the P. So to make F is equal to 50 Hz, increase the number of poles, and the minimum number of poles which you can see in a practical 7-pole alternator is always 12. So you cannot see less than 12. The minimum value is 12. So more than that only you can see in the general case in the world. So therefore, the minimum value number of poles of 7-pole alternator is always 12. You cannot see less than that. So this 7-pole alternator is always used in the hydropower station. So this 7-pole alternator is always used in the hydropower station, and the shaft is arranged in vertical configuration. It is used in the vertical configuration because in hydropower station, turbine can give maximum efficiency in the vertical configuration itself. So you can see clearly, if you go to any power plant, you can see clearly they are going to keep like this. The alternator will be in a downward fashion. It will be like placing downward. So the shaft will be in the upward direction. So water is going to come flow from upward and it is going to get the shaft. So therefore we can say it will be always in the vertical position. So shaft will be always kept in the vertical position. So therefore it is preferred in the hydropower station and the shaft is arranged in the vertical configuration. So this is what I mean. This is what I mean, which is called as the vertical configuration. Shaft will be like vertical and the stator is going to kept on the ground. So you can see they are going to keep in the ground like this, stationary in horizontal fashion, and this is called as the rotor. So rotor is kept in the, or you can see the shaft is kept in the vertical direction. So water is going to go inflow here and it is going to rotate this turbine. So therefore we are going to produce the electrical energy. So if you keep the shaft in the vertical position, there will be maximum efficiency in these turbo alternators. So therefore we can say that it is preferred in the hydropower station and the shaft is always arranged in the vertical configuration, because in hydropower station turbine can give maximum efficiency only in the vertical configuration. That is the reason we are going to keep the shaft in the vertical configuration, and this is the stator. It is like in a horizontal fashion. So by providing the pole shoe, flat topped waveform, which is called the trapezoidal, is obtained. So by providing the pole shoe, flat topped waveform trapezoidal is obtained. To obtain sinusoidal induced voltage, chamfered pole is provided. So chamfered pole is provided. So therefore it is designed such that at center of pole, air gap length is minimum. From center of pole to an outward of the pole, air gap length increases. So here this means that by providing pole shoe, flat top waveform trapezoidal is obtained. So if you provide a pole shoe, for the poles, we are going to get a trapezoidal. Now, like a flat top waveform is also called as a trapezoidal waveforms are going to induce in the voltages. If you want to obtain the sinusoidal induced voltage, chamfered pole is provided. So if you provide a pole shoe, for a pole, the waveform we are going to get is a trapezoidal waveform, or the flat top waveform we are going to get in the induced voltage in the coils. But if you go for the chamfering of the folds, then we are going to get a sinusoidal induced voltage is going to get, we are going to get. It is designed such that at the center of pole, air gap length is minimum. From center of pole to an outward of the pole, the air gap length increases. So we can, I've already told this important point, which is always that there is a irregular of air gap between the rotor and the shaft. There is no uniform air gap between the stator and the rotor. So if you provide the pole shoe for the pole, then we are going to get a flat top waveform or trapezoidal waveform, the induced voltages. But if you do the chamfering of the folds, then we are going to get the induced voltages. And I already told you there is no uniform air gap between the stator and the rotor in a 7-pole alternator. The alternator, by providing the damper windings, transients are reduced and the negative sequence field is suppressed. It's a very important point. I will discuss these things in a later in a more detailed manner. Why damper windings are used for what is the reason for behind that one. So in the alternators, by providing the damper windings, we are going to eliminate the transients are reduced and the negative sequence field is also being suppressed. So if you use a dampering winding, on the rotor, we are going to reduce the transients and also the negative sequence field is also being suppressed with the help of this one. So therefore we can say simply, if you use the damper windings on the rotors of the 7-pole alternator, we are going to reduce the transients and also we are going to suppress the negative sequence fields have been suppressed. We will discuss something more about this one in the coming classes. These are some of the important points regarding the silent pole alternator. So these are some of the important points regarding the silent pole alternator concepts. So now we will discuss about the cylindrical pole alternator. In the previous one we have learned about the silent pole alternator, but we are going to discuss now about the cylindrical pole alternator. Cylindrical pole alternator means the rotor will be in a circular fashion. The rotor will be in the circular shape. Whereas in the previous case, the rotor was like it has some projected poles, whereas here the rotor is a purely circular fashion. So therefore, the rotor is a solid, the rotor is made of a very solid material and it is going to have circular fashion. So whenever it is circular fashion, simply we can say that the diameter will be very less. So therefore, the axial length will be very high. So therefore, we can say that this is a cylindrical pole alternator will have the circular rotor with a less amount of diameter, but the axial length will be very higher. So you can see clearly this is the south pole and this is the north pole. So this is the winding we can use to get this type of the poles. So in the entire outer periphery of the rotor, 2/3 portion is arranged with the slots and 1/3 portion forms as a poles. So in this rotor, 2/3 of the portion is arranged with the slots. The slots is used for winding and the remaining 1/3 is portion for the poles. So therefore, we can say in the entire outer periphery of the rotor, 2/3 portion is arranged with the slots and 1/3 portion forms as a poles. So due to absence of projected poles, it is having a smaller diameter, so the long axial length is going to get obtained. So to obtain the required power in the stator slots, lengthy connectors are provided. Because I have already told you here, we are going to get small amount of diameter because there is no projected poles. So therefore, we are going to use the large amount of axial length to improve the power. So this is some of the detailed concepts of the cylindrical pole alternator. The rotor is made of a solid. Here we can see that 2/3 portion of this rotor outer periphery is filled with windings, is filled with slots, and remaining 1/3 is used for the formation of the poles. And there is no projected poles, so we can the diameter is very small and has a large amount of axial length. So therefore, we can use large amount of lengthy conductors. I have already told you the power is directly proportional to square of diameter into length of the axial length of this rotor. I already told this important expression, which is power is always directly proportional to square of the diameter of the rotor into length of the axial length of the rotor. So if the diameter is very less, then definitely we have to increase the length to make the power as a constant. So therefore, whenever the diameter is less, we have to use the large amount of lengthy conductors to get the constant power. I have already told you here, length is always greater than the diameter, so length is nearly equal to 5 to 7 times the diameter, whereas in the previous case, diameter was nearly equal to 5 times the axial length, whereas in this one it is quite opposite of the previous one, which is the length is nearly 5 to 7 times the diameter of the rotor. So to obtain the electromagnets, distributed winding is provided. So if you want to provide the electromagnets on this rotor, then definitely you have to use the distributed winding. we have to use the distributed winding but not a concentric winding. So in the previous case we have to use the concentric winding to get the poles, but here we have to use the distributed winding. So uniform air gap length is present between the stator and the rotor. Because the rotor is a circular fashion, we can say at any point on the rotor, the distance between the perpendicular distance between the stator and the rotor is always constant, irrespective of the position where you are going to stay on the rotor. We can say it is having the uniform air gap. In the small diameter, it can be operated at very high speed. So as the diameter of the rotor is very less, then definitely the diameter of the stator will be also less. So you can operate the rotor at a very huge amount of speed. At very huge amount of speed you can operate. So therefore, to obtain the rated frequency, less number of poles are required, because I have already told you NR is equal to NS is equal to 120 F by P. If you manipulate this one, we are going to get F is equal to Pn by 120. As N is very higher, so you have to decrease the P to make the frequency as a constant. So the minimum number of poles are 2. So therefore the minimum number of poles are 2 on this cylindrical pole alternator. So on the cylindrical rotor, the minimum number of poles are 2. So therefore we can simply say that it is the minimum value. So poles are always an even number. You will never get an odd number of poles. Always poles are going to get in a double pair, or you can say in a pair fashion they are going to come. So it will be never be an odd number, it will be always an odd number. Whereas in the previous case, the minimum number of poles are 12, whereas for here the minimum number of poles are 2. It is preferred with thermal and the nuclear power stations with horizontal shaft configuration. In thermal power station, turbine can give maximum efficiency with horizontal shaft configuration. So whereas in the silent pore alternator, it is used in the hydropower generation and the shaft is kept in the vertical direction, whereas here this type of the cylindrical pole alternators are used in the thermal and also in the nuclear power stations, and the shaft of this rotor is always kept in the horizontal direction, because in the direction itself only the maximum efficiency can be produced by the thermal power station turbine. So that is the reason we prefer to keep the shaft of the turbine of this cylindrical pole alternator in always in a horizontal position. So we can say that it is preferred in thermal and nuclear power stations with the horizontal shaft configuration. In thermal power station, turbine is going to give you the maximum efficiency with the horizontal shaft configuration. So this is what I mean. Here the shaft is in the horizontal direction. So if you keep in the horizontal direction, the turbine of the thermal and the nuclear power station can give maximum efficiency only in the horizontal direction. So therefore we can simply say that the silent pole alternator is used in the hydropower generation, whereas the cylindrical pole alternator is always used in the thermal and also in the nuclear power stations. For the rotor core, no laminations are required. So therefore for the rotor core, no laminations are provided. So therefore we can say that for this case, the rotor core, we don't have to keep any laminations. So no laminations are provided for this rotor core. So we can simply say that there is no requirement of the laminations for this rotor core in the cylindrical pole alternator. These are some of the important points regarding the cylindrical pole alternator. So now we will discuss about the another important concept and we will see what is going to happen. Suppose this is the stator and this is the rotor. In the stator, I am going to use the armature conductors of three phases: R phase, Y phase and B phase. Whereas on the rotor, I am going to use like this, which is called as this type of rotor is always called as a silent pole rotor. So I am going to use the external winding in such a fashion. So therefore, I am going to give the DC supply. So therefore, here we are going to get the north pole and here I am going to get a south pole. You can easily apply the right hand thumb rule. If you curl your fingers in the direction of the current, the thumb is going to show you the direction of the flux. So here it will be a north pole and it will be a south pole. Then what I am going to do, basically I am going to rotate this rotor. I am going to rotate this rotor with the help of a shaft. So we can say with the help of prime mover, I am going to rotate this rotor. Then definitely as it is moving in the clockwise direction, this R phase is going to cut the flux is going to cut the initially R phase, then comes the Y phase and then comes the B phase. So what is the phase sequence? R, Y and B. So this is the R, this is the Y and this is the B. So let me assume this is called as a positive phase sequence. If I rotate the rotor in the clockwise direction, the flux is going to initially cut the R phase, then comes the Y phase, then comes the B phase. So the amount of EMF will be first induced in the R phase, then comes the Y phase, and then comes the B phase. So what is the phase sequence which is called as the R by B? So let me assume this is called as the positive phase sequence. So now what I will do basically, I will reverse the supply voltage. I will reverse the supply voltage to the field winding, and then I will rotate in the same direction, and I will see what is the consequences which is going to occur. So same thing, I have just interchanged the supply voltage, and same thing in the same direction I am going to rotate the rotor, and then I will see what is the things are going to happen. So same thing, I have interchanged the supply, so current is going to get change its direction, but the field winding direction is same. So if you apply the right hand thumb rule, then if you curl your fingers in the direction of the current, and the thumb is going to give you downward, so this is north pole and this is south pole. So in the previous case it was reverse. If you change the polarity of the supply voltage, the polarity of the induced voltage also are going to get interchanged. So now I am going to, in the same direction I am going to rotate the shaft, or I am going to rotate the prime mover of the shaft of the rotor. Then definitely we can see clearly the B phase is going to, the B phase values is going to initially cut the flux, then comes the R phase, and then comes the Y phase, and then comes the B phase. So like this you are going to get. So initially B phase, then R phase, then Y phase, and then B phase. So you can see clearly again there is a RYB sequence. So there is again RYB sequence, same as the previous one. So therefore again it is a positive phase sequence. So we can say that even if you change the polarity of the supply voltage for the field winding, and the rotation of the shaft is still the same, there is no change in the phase sequence. There is no change in the phase sequence. That is the meaning of this concept. Even though you are going to change the supply voltage polarity of the field winding, the phase sequence of the voltages is not at all changed. It is always the same, because you can see there also RYB, here also RYB. So phase sequence is not changed. But if you want to change the phase sequence, you don't have to change the supply voltage of the field winding, just you have to change the rotation of the shaft. Rotational direction of the shaft you need to shift. You need to change. Generally the phase sequence is going to get changed. So we will see how it is happening like that. Same figure in the first case. Now same voltage, same polarity, with the same winding, everything is same. So this is the current, and if you curl your fingers in the direction of the current, and if the thumb is going to give you showing the direction of the flux. So this is north pole and this is the south pole. This is the R phase and this is the Y phase and this is the B phase. So now I have interchanged the rotation of the shaft of the rotor. Then the R phase is going to initially cut the flux. So EMF is going to induce initially in the R phase, then comes the B phase, and then comes the Y phase. Then what is the phase sequence, which is R, B and Y. So R, B and Y. So therefore if R, Y, B in clockwise, it is called as the positive phase sequence, and this is R, B, Y. So the phase sequence is reverse of the previous one, so it is called as the negative phase sequence. It is called as the negative phase sequence. So simply we can say that this is said to be negative phase sequence of the previous one. So therefore we can say that if you want to interchange the phase sequence of the induced voltages, if you want to change the phase sequence of the induced voltage in the stator winding, definitely you have to change the rotation of the shaft of the rotor, but not be interchanging the supply voltage field winding supply voltage terminals. This is a very important point that you always have to understand. So therefore the only thing, the final conclusion is, if you want to change the phase sequence of the induced voltage in the stator coils, or simply we can say armature coils which are placed on the stator, you have to interchange the direction of the rotation of the shaft of the rotor, and you don't have to change the remaining things. So from figure 2 and figure 3, so from figure, so this is a figure 1 and figure 2. So from figure 1 and figure 2, it is considered that by reversing the polarity of the field winding, phase sequence does not change. And what I told you in the figure 1 and in the figure 2, just by reversing the polarity of the field winding, the phase sequence will never change in the stator coils. So we can say in the armature coils which are based on the stator. So from figure 1 and figure 2, we can see that it is considered that by reversing the polarity of the field winding, phase sequence does not changes. But from figure 1 and figure 3, it is concluded that by reversing the direction of rotation of rotor, the phase sequence can be reversed. This is a very important conclusion from this concept, which is from figure 1 and figure 2, we can see that even though you are going to interchange the field the field winding supply voltage, you are not going to get the you are not going to reverse the phase sequence of the induced voltage in the armature coil which are placed on the stator. But if you see from figure 1 and figure 3, you can easily see that just by interchanging the direction of rotation of the shaft of the rotor, you are going to get the negative phase sequence. So this is the concept that you need to always understand. So if you want to change the phase sequence of the induced voltage in the armature coils which are placed on the stator, just change the rotation of the shaft of the rotor. So now we will discuss about the new concept which is called as the effect of AC supply on field winding. So effect of AC supply on the field winding. Suppose if I give AC supply to the field winding and then I want to know what are the consequences because of this one. Suppose let me assume this is called as a stator and this is the rotor. The rotor is basically, you can see clearly it is a 7-pole rotor. So therefore I am going to give an AC supply for this winding, for this field winding. If I am going to give the AC supply on the field winding, then let me assume for the positive half cycle, the current in this direction. So if you apply the right hand thumb rule, then if current is inward, if you apply the right hand thumb rule, if you curl your fingers in the direction of the current and the thumb is going to show you the direction of the flux. So this is the north pole and this is the south pole. So let me assume the conductors which are near the north pole will have the current entering them, whereas the conductors near the south pole will have the current which is leaving them. So here it is cross means entering, here dot means they are leaving. So we can say that, see, this is called as the TP is called as the mechanical torque. Means I am going to do the rotation of this. I am going to do the rotation of this rotor. And this is called as the electromagnetic torque, or we can say this is the electrical torque. This is the mechanical torque and this is the electrical torque. So electrical torque is always going to oppose the mechanical torque. So by this torque I am trying to rotate in the clockwise direction, but electrically there will be one more torque which is opposing the motion of this mechanical torque. This is called as the electrical torque. So this is the consequences we are going to see for the positive half cycle. And now we will see what happens for the negative half cycle. So now again for the negative half cycle, what is going to happen is basically for negative half cycle means the current in the previous case is entering but now it is leaving. So if you apply the right hand thumb rule, if you curl your fingers in the direction of the current, the thumb is going to show the flux. So now the fluxes are going to interchange. Down will be north pole and upward will be south pole. I already told you whatever the conductors near the north pole will have current which is entering them, and near the south pole the current is leaving them. All these things I have already told you. So therefore, in the same direction I am going to rotate the shaft in the clockwise direction, but now the electrical torque is going to get interchanged. Previous it is in this direction, but now it is in this direction. So therefore we can say that it is going to in the same direction of the mechanical torque. So therefore we can simply say which is called as the, so when AC source is connected to the field winding, rotor continuously subjected to forward and the backward electromagnetic torque. So net, whenever the AC source is connected to the field winding, the rotor is continuously subjected to forward and the backward electromagnetic torque. So net electromagnetic torque is equal to 0 and no energy conversion is present, and see output voltage is equal to 0. See, whenever you give the AC source, so whenever you apply the AC source to the field winding, so definitely the rotor for the positive half cycle, the electromagnetic torque is in the other direction, and for the negative half cycle the electromagnetic in the reverse direction. So the average amount of electromagnetic torque which is absorbed by this rotor is equal to 0. So when electromagnetic torque is equal to 0, which is absorbed by the rotor, so no energy conversion is present between the stator and the rotor. So definitely, so output voltage will be always equal to 0. That is the reason we have to give only the DC supply but not the AC supply. If you give the AC supply, the output voltage will be always equal to 0 in the armature coils are placed on the stator. So whenever the AC source is connected to the field winding, the rotor is continuously subjected to the forward and the backward electromagnetic torque. So net amount of electromagnetic torque which is absorbed on the rotor is equal to 0. So no energy conversion is present between the stator and the rotor. So definitely the amount of output voltage which is induced in the armature coils which are present on the rotor will be always equal to 0. This is a very important concept. That is the reason you don't have to apply the AC voltage for the field winding, but you have to apply only the DC voltage to the field winding. So whenever you apply AC voltage, AC source to a, whenever if you apply the AC source to a field winding, definitely the rotor is going to continuously subjected to a forward and the backward electromagnetic torque. So net amount of electromagnetic torque is absorbed by the rotor is equal to 0. So no energy conversion is present between the stator and the rotor. So definitely we can say, so no output voltage is going to induced in the armature coils which are present on the stator. So therefore the output voltage will be always equal to 0. Now we'll discuss one more concept regarding this synchronous generator. Suppose let me take a silent pole alternator, or simply we can say the rotor is in the format of the projected poles. This is the north pole and this is the south pole. After removing the concentric winding on this pole, I am going to get which is electromagnet of north pole and south pole. So you can see clearly this is the stator and this is the rotor. So therefore this north pole is going to generate a flux which is in this direction, because north pole is always going to eject the flux. So this is called as the field flux, because the field winding is present on the rotor, it is going to generate the flux. This is the direction of the field flux. Let me assume this is the direction of the field flux phi f, and I am going to rotate the shaft. I am going to rotate the shaft of the rotor in this anti-clockwise direction, or simply we can say it is in the anti-clockwise direction. So Tp is the mechanical torque by which we are going to rotate the rotor in this anti-clockwise direction. So always EMF, we can say EF is called as the EMF induced in the field winding. It is always equal to the terminal voltage. So therefore here the EF is always going to lag the flux by 90 degree. So EF is called as the induced voltage. So basically EF is called as the induced voltage, or we can say it is the induced voltage in the stator coils. EF is called as the EMF which is induced in the we can say the armature coils which are placed on the stator. So always it is going to lag the flux by 90 degree. So you can see clearly here. So now I am going to apply the Fleming right hand rule, because for generator we have to always apply the Fleming right hand rule, because here there is a R, in the right hand also there is a R. So that is the reason we have to use the Fleming right hand rule. In the Fleming right hand rule, the thumb is going to represent the force and the forefinger is going to represent the magnetic flux density, whereas the middle finger is going to show the current. So therefore the forefinger is going to show the flux, thumb is going to show the force or mechanical torque, and middle finger is always going to show the current. So therefore FBI, thumb means force or torque, and the forefinger means flux or magnetic flux density, and then middle finger is the current. So this is the notation of the Fleming's right hand rule. So by this you can figure out the current induced here you can easily figure out in the coils which are present near the north pole and which are present near the south pole. Remember this formula, still you can apply the basic principle, which is F cap is equal to I cap cos B cap. Here F cap is nothing but it is an electromechanic, it is an electromagnetic force but not the mechanical. So electrical is always opposite to the mechanical. So by this principle you can apply that small equation also. You can give the direction in the conductors near the north pole and south pole. You can easily figure it out. If you apply the right hand thumb rule here, so the Fleming's right hand rule, the flux in this direction and the torque is in this direction. So therefore if the forefinger is in this direction and the thumb is in the downward direction, so therefore the middle finger is inward. So simply we can say that near the north pole the current carrying by the conductors near the north pole will be inside. Here it is quite opposite. So conductors near the south pole will have the current which is leaving them. So thumb is called as a mechanical torque you need to consider. It is a mechanical torque you need to consider. So with the help of Fleming right hand rule you can easily figure out the direction of the current in the conductors near the north pole and the south pole. So I have already told you the conductors near the north pole will have the current which is inward, and the current near the south pole will have the conductors which are near the south pole will have the current which is leaving them. Suppose for the lagging load what is going to happen, basically now we are going to see for lagging load what is going to happen. Suppose if you apply the lagging load to the armature coils which are present on the stator, then definitely the current is going to lag the voltage it is supplying them. So EF is called as the induced voltage in the stator coils, or simply we can say the armature coils which are present on the stator. So EF, this current is going to lag them, so current is going to lag by a small amount of angle theta. So theta is called as the load angle, or simply we can say it is a power factor of the load. So theta is a power factor angle of the load. So by this theta it is going to lag here. So this is the current IA. So if whenever the current IA, that it is called as the IA is the current which is flowing in the stator coils, then definitely it is also going to produce an amount of flux. It is called as the armature flux. It is called as the armature flux, and this is the field flux. I have already told you this is the north pole and this is the south pole. I have already shown this is for the rotor. This is the north pole and this is the south pole. So these are the poles which are correspond to the rotor. So now I am gonna do some important thing which is called as the the resultant flux. So if I do the vector addition of this phi f and the phi a, the overall flux is called as the resultant flux, or we can say the air gap flux. This is called as the air gap flux. So if you see clearly that this is called as the air gap flux. So phi f is always going to lead the phi air gap flux. So therefore this phi f is always going to lead the resultant air gap flux, or simply we can say this phi f is always going to lead the resultant air gap flux, and the resultant air gap flux is always going to lead the phi a. So phi f is going to lead the resultant air gap flux, and the resultant air gap flux is going to lead the phi a. So this is a very important point that you always need to understand. So this field flux is always going to lead the resultant air gap flux, and the resultant air gap flux is always going to lead the phi a. Phi a is called as the armature flux. I am going to do the component method. So I am going to decompose into two vectors. Here it is the AB. So AB is nothing but which is IA cos theta. So IA cos theta, it is responsible for the generator output. So whenever the current which is in phase with the supply with the induced voltage in the stator coils, that is responsible for the generator output. So IA into cos theta, it is the responsible for the generator output, because whatever the current which is in phase with the EMF induced in the stator coils, they both are responsible for the production of the output in the generator. So simply we can say that phi f is going to lead the resultant air gap flux, and the resultant air gap flux is going to lead the armature flux. So now if I draw these things, you can see clearly this is a field flux. So field flux in this direction. So this is north pole and this is south pole. I have already shown you this is the north pole and this is the south pole. And the electric, or we can say the mechanical torque is in this direction. So therefore we can say this is called as the armature flux. So this is armature flux in this direction from down to up. So therefore this will be north pole and this will be south pole. So therefore this is the north pole and this is the south pole. So therefore here it is the north pole and it is south pole for the poles corresponding to rotor, and this is in this direction. So this is north pole and this is the south pole. So this is the, we can say this is the north pole and this is the south pole. So therefore flux is moving from north pole to south pole here. So we can say clearly these are the poles which are corresponding to the stator, and these are the poles which are corresponding to rotor, because flux travels from north pole to south pole outside. So therefore this is the north pole and this is the south pole. So these are the poles corresponding to the rotor, and these are the poles corresponding to the stator. If you see clearly, these are the like poles and these are the like poles. So like poles are always going to repel. So here also the like poles are going to repel. So therefore there is a repulsion between these poles and there is a repulsion between these two poles. I have already told you that mechanical torque which was on the rotor is always in the clockwise, means I am going to rotate the rotor in the clockwise direction. So there is a repulsion. So repulsion means the electrical torque is going to oppose the mechanical torque. So always the electrical torque is always going to oppose the mechanical torque in the generator. So always because of the repulsion, the electromagnetic torque is always going to oppose the mechanical torque. So this is a very important concept that you always have to understand behind this one. So this diagram I have drawn in the air gap region, because in the air gap region I have drawn this two flux direction. So we can see clearly the mechanical torque and the electrical torque are quite opposite because of this repulsion force. So therefore we can say that simply EF is called as the EMF which is induced EMF voltage on the stator coils or the armature coils which are present on the stator, and V is called as the terminal voltage across the load. I am going to assume zero voltage drop across the internal impedance. So EF is nearly equal to V, but practically it is not the case. So phi F is called as the main field flux, and IA is called as the current in the stator coils on the yoke. Or simply we can say it is the current in the stator coils or the armature coils which are present on the stator. So this is a very important notation. So therefore EF is called as the induced voltage in the armature coils which are present on the stator, and V is called as terminal voltage across the load, and phi F is called as the main field flux, and IA is called as the current in the stator coils on the yoke. So this is a very important concept. So finally we can say that in a synchronous generator, the electromagnetic torque is always quite opposite to the mechanical torque. So this angle between them, the angle between these two fluxes, the angle between these two things is called as the delta. The delta is called as the load angle. So this is the phi f and this is the phi a. The acute angle between them is called as the load angle. The acute angle between the armature flux and the field flux, it is called as the load angle. So now we will understand the same concept for the synchronous motor. Up to now we have learned about the synchronous generator. Same concept we are going to apply for the synchronous motor, and we will see what is going to actually happen. So this is the synchronous motor. So this is the stator and this is the rotor. Same thing, the rotor we are going to give a field winding. So we are going to give a field winding to this rotor. It is basically silent pole rotor. So therefore here we are going to get north pole and the south pole. So the flux will be from outward. If you see outward from north pole, the flux is going to eject outward. So therefore this is the phi f. So this is the phi f. I have already told you the EMF which is induced in the stator coils is nothing but it is going to lag the field flux by 90 degrees. So this is the EF. And similarly again I am now here the rotor should rotate. Let me assume the torque which is produced on the rotor is TP in this direction. So now we will do analysis of this one in a very detailed manner. So now I have already told you this is the phi f and this is the EF. So now this you have to do the reverse process of the previous case. So in the previous case the IA was here, for lagging load here it is outward, but now just do the reverse process of 180 degrees. So you are going to get downward. So this is the current IA you are going to get. So this is the current I just the motor analysis quite reverse of the generator analysis. So this is a very important point. The motor analysis is quite opposite to the analysis of the generator. So here it is downward IA. So IA is going to produce the armature flux. So therefore this is the phi A flux. So therefore if you draw a straight line, so this is the called as the angle theta. So this is called as the angle theta, and this AB is nothing but IA into cos theta. So you can see clearly the armature flux is going to lead the field flux, and if you do the resultant of these two vectors, it is called as the resultant air gap flux. So the armature flux is going to lead the resultant air gap flux, and the resultant air gap flux is going to lead the field flux. So this is the quite important notation that you need to always understand. So if I draw it in another phase, so this is the north pole and this is the south pole. This north pole is going to give a field flux in this direction, and here the flux in this direction. So north pole is here and south pole is here. So north pole is here and south pole is here. So this is going to give a flux of armature flux phi A in this direction. So now we can see clearly these are the poles which are induced on the rotor, and these are the poles which are induced on the stator. So this is the north pole and this is the south pole. So unlike poles are going to get attract. Here it is the north pole and it is the south pole. So unlike poles are going to get attract. So there will be attraction between the poles corresponding to the rotor and the stator. So therefore the electrical torque is in the same direction of the mechanical torque. So this is a very important point here. Whereas in the synchronous generator, the electrical torque is opposite to the mechanical torque. Whereas here the mechanical torque and the electrical torque are in the same direction. Is called as the IA into cos theta. So AB is called as the IA into cos theta. So this is going to oppose this EF. So you can see clearly this AB is nothing but IA into cos theta. This vector is going to oppose the EF. It is going to oppose the vector EF. And phi F is called as the main field flux, and phi A is called as the armature flux, and phi A is going to lead the phi F and also the resultant air gap flux. So armature flux is going to lead the resultant air gap flux and also the field flux. So this analysis is quite opposite to the generator analysis. Delta is the acute angle between the field flux and the armature flux. So therefore delta is the acute angle between the field flux and the generator, or we can say the armature flux. Because of these two flux, there is a distortion in the resultant air gap flux. It is called as resultant air gap flux. This process is called as the Rotor reaction. So AB is called IA into cos theta. It is going to oppose the EF, and phi F is called as the main field flux, and phi A is called as armature flux, and phi A is going to lead the phi F and the resultant air gap flux. So now we will understand the important points regarding the synchronous generator and the synchronous motor in a very detailed manner. So when the active component of current is in the phase with the voltage, then machine is going to behave like a synchronous generator. All these things I have already told you. whenever the Ia into cos theta is in phase with the EF, then we can say it is said to be, synchronous generator. So when active component of current is in the phase with the voltage, then machine is going to behave like a synchronous generator. So therefore simply we can say whenever the Ia into cos theta is in phase with the EF, then we can say it is said to be synchronous generator. So whenever the active component of the current, which is Ia into cos theta, is in phase with the voltage, then we can say that machine is going to behave like a synchronous generator. If it is opposite, means it is a synchronous motor. So in the synchronous generator action with respect to main field flux, air gap flux is lagging. So air gap flux is lagging, and also with respect to air gap flux, armature flux is lagging. And already told you the resultant air gap flux is going to lag the field flux, and the armature flux is going to lag the resultant air gap flux in the synchronous generator. So in the synchronous generator action with respect to main field flux, the resultant air gap flux is going to lagging, and with respect to air gap flux, therefore the armature flux is lagging. All these things I have already told you. In the synchronous generator, the electrical torque is always opposite to the direction of the rotation of rotor. So therefore T2 is called as the mechanical torque, which is responsible for the rotation of the rotor, and the T is called as the electrical, or you can say electromagnetic torque, which is quite opposite to the rotation of the mechanical torque. So therefore in the synchronous generator, the electrical torque is quite opposite to the direction of rotation of rotor. Synchronous generator action, load angle is measured between the similar poles. I have already shown this in the graph itself. So there is a two north poles and there is a two south poles which are present near to by each other. So there is a repulsion between them. So we can say that delta is the load angle between the two similar poles. So delta is the load angle between the two similar poles in the synchronous generator, but it is opposite for the synchronous motor action. So in the synchronous generator action, the load angle is measured between the two similar poles because of repulsion. To obtain the electromagnetic torque, the number of poles in the stator and the rotor should be always equal. So if you want to obtain the electromagnetic torque, the number of poles in the stator and the rotor should be equal. This is a very important point. See, always the number of poles which are induced on the rotor, on the stator and the rotor should be always equal. Then only this electromagnetic torque is going to get produced. Otherwise, electromagnetic torque will never produce. So always to obtain the electromagnetic torque, the number of poles in the stator and the rotor should be always equal. Then only we can say that this is going to, the electromagnetic torque is going to get obtained. So to obtain the electromagnetic torque, the number of poles in the stator and the rotor should be always equal. So to obtain the electromagnetic torque, the number of poles in the stator and the rotor should be always equal. Then only the electromagnetic torque is going to get obtained. So when the active component of current is antiphase to the voltage, then machine is going to behave like a motor. I have already told this point. So whenever the active component of the current is in antiphase, it is quite opposite to the EMF induced in the armature coils present on the rotor, then we can say that machine is going to act like a motor. In the motor action with respect to main field flux, so in the motor action with respect to main field flux, the air gap flux is leading, and with respect to air gap flux, the armature flux is leading. All these things I have already shown in the figure of the synchronous motor. So therefore, in the synchronous motor action with respect to main field flux, the resultant air gap flux is leading, and with respect to air gap flux, the armature flux is leading. And also in the synchronous motor action, electromagnetic torque is developed in the same direction of rotation of motor, and the load angle is measured between the two dissimilar poles. In the synchronous motor action, electromagnetic torque is developed in the same direction of rotation of the motor, and the load angle is measured between the two dissimilar poles. Whenever there are two dissimilar poles, there is an attraction. So therefore, TP and TE are going to present in the same direction. So therefore, the electromagnetic torque is going to produce in the same direction of the rotation of the rotor. So because of this electromagnetic torque only, the rotor is rotating. So we can say because of this electromagnetic torque only, the rotor is rotating. So therefore, we can say in the synchronous motor action, the electromagnetic torque is developed in the same direction of the rotation of the motor, and the load angle is measured between the two dissimilar poles. Whenever two dissimilar poles are there, there is an attraction. So therefore, the mechanical torque and the electrical torque are in the same direction. So now we discuss one more important concept, which is called as the armature reaction on the synchronous generator or alternator. See, whenever the main field flux and the armature flux are going to interact with each other, then definitely there is a distortion in the overall resultant air gap flux. That is called as the armature reaction. So whenever the main field flux and the armature flux, whenever both are going to interact with each other, therefore there is a distortion in the resultant air gap flux. That is called as the armature reaction. So we are going to see what is the nature of the armature reaction in the synchronous generator, because it is also called as the alternator. Suppose if I consider a zero power factor lagging load, it means simply it is a purely inductive load. Suppose if I keep a purely inductive load to the stator coils, then definitely what is going to happen, I already told you, this is called as a field flux, and this is the EMF which is induced in the stator coils, and this is called as the terminal voltage. If I assume that there is no voltage drop in the stator coil, definitely we can say EF is nearly equal to V, and we are going to keep the lagging load, so therefore IA is going to lag the EF by 90 degree. Then what is the, see, this IA is going to produce the armature flux, so IA and phi are going to phase with each other. Then the resultant, we can say the resultant angle between the phi f and phi a is nothing but here, in this case, which is 180 degrees. So what is the resultant air gap, which is phi f minus phi a, because this will be very higher when compared to this value. So therefore the resultant air gap is equal to phi f minus phi a. So this is called as a demagnetizing, because the resultant air gap flux is decreased. So it is called as the demagnetization. Demagnetization means simply we can say that if the resultant air gap flux is a decrease, it is called as the demagnetization effect. So demagnetization effect is going to occur if you keep a purely inductive load for this synchronous generator. So phi f is called as the main field flux, which is produced by the rotor poles, and phi a is called as the armature flux, which is produced by the stator coils, and EF is called as the EMF, which is induced in the stator coils, and V is called as the terminal voltage of the induced, the terminal voltage of the stator coils. So therefore we can say whenever the load increases, whenever the purely inductive load increases, the current IA increases. As the current IA increases, the armature flux increases. So therefore the resultant air gap flux decreases. If the resultant air gap flux decreases, the EMF is also going to decrease, because EMF is going to depend upon the flux. So therefore as this resultant air gap flux decreases, the EMF induced in the stator coils is going to decrease. If the resultant induced voltage decreases, means the terminal voltage is also going to get decreased. So this is the point that you need to understand. So in a purely inductive load, if the load current increases, if the load increases, the armature current increases. So therefore the armature flux increases, so resultant air gap flux decreases. So EMF induced in the stator coil decreases. So terminal voltage of the stator coils are also going to get decrease. So this is the concept for the zero power factor lagging load, or simply we can call it as the purely inductive load. Now suppose if we keep the zero power factor leading load, means purely capacitive load. Suppose if I keep a purely capacitive load to the stator coils of the synchronous generator or alternator, what is the consequences which are going to occur? So therefore this is called as the field flux, and this is called as the EMF, which is induced in the stator coils. It is nearly equal to the terminal voltage. As it's a leading load, so definitely current IA is going to lead the EF. So this current is going to lead the EF. So IA and phi a, because IA is going to produce the armature flux, both are always phase with respect to each other. So we can say phi f is in phase with phi a. Then what is the resultant air gap flux? It is the summation of the individual fluxes, phi f plus phi a. So therefore the resultant air gap flux is the summation of the field flux and the armature flux. So we can say it is said to be magnetization, because the overall flux is increased. The overall flux is increased means it is called as the magnetization. If the overall flux decreases, means it is called as the demagnetization. So we can say clearly, whenever the capacitor load increases, the armature current increases. So therefore the armature flux increases. So therefore the resultant air gap flux increases because of the addition property. So therefore the EMF induced in the stator coils increases. It means that the terminal voltage of the stator coils is also going to get increased. So this is the consequences which are going to happen for the capacitor load. It's a very important point. So this you need to always analyze, because based on this only we are going to draw the graphs for different types of loads. If you are going to connect the different types of tests on the synchronous machines. So I request you to remember this concept, so therefore it is very much useful in drawing the graphs for doing the tests on synchronous machines and figuring out all the different graphs for different applications. All these things I will discuss in a later, but up to now you have to understand this concept. So therefore whenever the load increases, whenever the leading load increases, the armature current increases, so the armature flux increases, so therefore the overall air gap flux increases, so therefore the EMF induced in the stator coils is increasing, so therefore the terminal voltage is also increases. Because what happens if I keep the purely resistive load, or we can say unity power factor load or purely resistive load to the stator coils, then what is going to happen? We can say simply this is the field flux and this is the EMF induced is nearly equal to the terminal voltage. As the resistive load, so IA is always in phase with the EF. So this is the IA. So IA and phi are always phase with respect to each other. Then the resultant is called as, if you do the vector addition of these two fluxes, we are going to get the resultant air gap flux. So you can, this is called the resultant air gap flux. So if you see clearly, this phi A is in the upward direction and phi F is in this direction. So therefore we can see in the left direction. So this is the phi F direction and this is the phi A direction. You can see clearly. So therefore it is cross magnetization. Cross magnetization means only there is a distortion of the flux. Only there is a distortion of the flux, but the flux is not decreasing its magnitude. So listen carefully. The flux is not decreasing its magnitude, only there is a distortion of the flux. The flux shape is going to get changed, but there is no demagnetization effect, means the flux is not decreasing. So therefore we can say there is only cross magnetization. Cross magnetization means only there is a change in the direction of the flux. Only the flux waveform is going to get changed, or we can say the flux in the air gap, the overall shape is going to get distorted, but the flux value will never change. It will never decrease or increase. So this is called as the cross magnetization. So this is called as the cross magnetization. So for a purely resistive load or unity power factor load, there will be only cross magnetization. There will be only cross magnetization. So we can see that for as load increases, as purely resistive load increases, IA increases, then phi A increases, then definitely the resultant air gap flux increases, then definitely we can say the EF increases, and definitely the V also increases, same as the previous case, because whenever the load increases, IA increases, phi A increases, then the resultant flux is also going to get increased, so therefore the EF increases and the V increases. So there is only cross magnetization. So finally I can say that for purely inductive load there is a demagnetization, for a purely capacitive load there is a magnetization, and for a purely resistive load there is only cross magnetization. Suppose if I apply RL load, then what is going to happen? If I apply RL load, the current is going to lag by a small amount of angle. So this is the field flux and this is the EMF induced in the stator coils. It is nearly equal to terminal voltage, and this is called as the current which is drawn. It is lagging by small amount of angle theta. Then if this is the current IA, then definitely the IA and phi A are always in the same direction. So phi A is called as the armature flux. If I do the two components, I am going to make it into two components. Let me assume this is AB and this is AD. So AB is equal to phi A into cos theta and AD is equal to phi A into sin theta. So you can see clearly phi A into sin theta and phi F are quite opposite of each other. So this is called as the overall flux is going to get decreased. It is called as the demagnetization. Whereas AB is nothing but phi A into cos theta and phi F are perpendicular to each other. So there is a distortion of the overall flux. So we can say that it is going to have the cross magnetization. So finally we can say because of RL load there is a demagnetization, there is also cross magnetization. These two effects are going to occur for this RL load. So therefore we can say whenever the phi A into cos theta and phi F are going to interact, there will be cross magnetization effects, means the overall flux is going to get distorted. Whereas phi A into sin theta and phi F are going to interact, then we are going to get the demagnetization effect, means the overall flux is going to decrease its magnitude. So we can say these two effects are going to occur if you keep a RL load to the synchronous generator or the rotor. So synchronous generator or the alternator. A very important point that you always have to remember in the concept is the cross magnetization is always directly proportional to the power factor. So cross magnetization is always directly proportional to the power factor. See, cross magnetization is always directly proportional to the power factor, and it is also directly proportional to the output power, and it is always proportional to the torque. So these are the three relations that you need to understand. So always whenever the cross magnetization is always proportional to the power factor, it is always proportional to the output power, and it is always proportional to the torque. The T is called as the torque and C is called as the cross magnetization effect, and PF is called as the power factor. Because if you see clearly, as the power factor of the load angle increases, if the power factor angle of the load increases, then definitely we can say that the power factor decreases Then if the power factor angle increases, then what is going to happen? The AD value will be very higher when compared to AD value. So AD is nothing but it is called demagnetization and AB is called as the cross magnetization. So definitely the cross magnetization effect will decrease and the demagnetization effect will increase. So therefore, whenever the cross magnetization effect decreases, then demagnetization will increase. So demagnetization increase means the resultant flux decreases. The resultant flux decreases means simply we can say the output power decreases and the output torque is also decreases. So finally I can say very important point, if the load power factor angle increases, then what is going to happen? Whenever the load power factor angle increases, then power factor of the load decreases. Whenever the power factor angle increases, the AD value increases and AD value decreases. AD is nothing but demagnetization, AD is called the cross magnetization. So whenever the AD value increases, the demagnetization effect will increase. So demagnetization effect will increase, and whenever the AB decreases means the cross magnetization effect will decrease. So that is the reason the cross magnetization effect decreases and the demagnetization effect increases. So whenever the demagnetization effect increases means the overall flux value, the magnitude value decreases. So therefore the output power decreases, because output power is a function of flux. As the flux decreases, its magnitude, the output power will also decrease. As the output power decreases, the torque is also decreases, because P is equal to T into omega. As P decreases, torque is also going to get decreased. So we can say the cross magnetization is directly proportional to the power factor, it is directly proportional to the output power, it is directly proportional to the torque. So you can see whenever the cross magnetization decreases, the output power decreases, the torque decreases and the power factor decreases. So you can see clearly from this explanation, that is the reason I have given these three important relations. So whenever the cross magnetization decreases, the power factor decreases, the output power decreases and the torque decreases. I have given a clear-cut explanation of each and everything. But now we will see different types of power factor of the load, and for the alternator and the synchronous motor we are going to visualize. See, the synchronous motor analysis is quite opposite to the alternator. If you remember this simple concept, then everything is same. Synchronous motor means just reverse, just to do the reverse of IA by 180 degree for the alternator. If suppose, if you want the same analysis for synchronous motor, for the same load analysis, just to do the reverse of the IA by 180 degree for the alternator, then you are going to get the analysis for the synchronous motor. If you understand this simple concept, then everything is very much easier. So remember carefully, if you want to, for a given load, if you want to analyze the alternator and synchronous motor, for synchronous motor, just to do the reverse of the area of the alternator by 180 degree and do the analysis, everything is same. So therefore, let me assume whenever the power factor of the load is unity power factor load, if it is connected to alternator, I have already told you only there will be cross magnetization effect. Similarly, go for the 180 degree, then current will be downward. So therefore again there will be same cross magnetization effect. Similarly, if you apply the zero power factor lagging, then phi f and phi r quite opposite of each other, so there will be demagnetization. But do the 180 degree change, there will be magnetization effect. For zero power factor leading load, then we can say both the flux are in the same direction altogether, so therefore there will be magnetization. But if it is the reverse, so therefore it will be demagnetization effect. So suppose if I take a lagging load of 0.8 power factor lagging, then definitely we can say there will be small amount of demagnetization, small amount of cross magnetization. So therefore partly demagnetization and partly cross magnetization. So both these effects are going to occur. So do the reverse of 180 degree, then you are going to get, now you are going to get like cross magnetization and also the magnetization. You are going to get cross magnetization and the magnetization. So partly cross magnetization and partly magnetization. Whereas if you keep the 0.8 power factor leading, then if you do the in alternator, there will be partly magnetization and partly cross magnetization. So partly magnetization and partly cross magnetization. If you go for the reverse process, if you go for the 180 degree phase shift, then definitely you can see there will be partly demagnetization and partly cross magnetization. So partly demagnetization and partly cross magnetization. So this is the analysis that you are going to get. I have already told you, for the given load, you can analyze the alternator from the above concept. The things that I have already told you. For synchronous motor, just reverse the current of IA by 180 degree and do the similar analysis. You are going to get for the synchronous motor corresponding analysis you are going to get. So this is what I am trying to tell you from this beautiful concept. So now we will discuss one more important concept, which is called as the lagging load connected to alternator. So what happens if we connect the lagging load to alternator? So what happens if we connect the lagging load which is connected to alternator? We are going to study this concept. So if we connect the lagging load to alternator, so what is the consequences which are going to happen? So we will see each and everything. So on the stator, we are going to keep the armature coil. So we are going to connect a lagging load to the alternator of the stator coils. Then the EMF induced is equal to per phase voltage. All these are called as the per phase voltage. So EMF induced is equal to terminal voltage plus IA into RA plus J into IA into XA plus XL. So this is the overall EMF induced equation in an alternator per phase voltage. So EF is equal to terminal voltage plus IA into RA plus J into IA into XA plus XL. Where XA is called as the reactance because of the armature reaction, and XL is called as the leakage reactance. So therefore we can say clearly this. So therefore EF, or we can write E1, and anyhow it is same. So therefore we can say that simply E1 is equal to V plus IA into RA plus J into IA into XL. So this V plus IA into RA plus J into IA into XL is called as the E1. So E1 is called as a V plus IA into RA plus J into IA into XL. So therefore, if we do simplification, we are going to get E1 plus J into IA into XA. So finally, we can say that XA plus XL is called as a synchronous reactance. The summation of the armature reactance plus the leakage reactance is called as a synchronous reactance, which is V plus IA into RA plus J into IA into XS. So this is a very important point that you always need to understand, which is EF is equal to V plus IA into RA plus J into IA into XA plus XL. This is the overall EMF induced equation in an alternator, where EF is equal to induced voltage per phase and V is the terminal voltage, and this is a drop in the stator coils. So therefore EF is equal to V plus IA into RA plus J into IA into XA plus XL. XA plus XL is called as a synchronous reactance. So finally we are going to get V plus IA into RA plus J into IA into XS. But E1 is called as a V1 plus IA into RA plus J into IA into XL. So finally we can write E1 plus J into IA into XA. So these are the different ways of writing the EMF induced in an alternator. So E1 is called as the air gap voltage, and E1 is called as the air gap voltage, and EF is called as the induced voltage per phase in a stator coil, and XL is called as the leakage reactance, and XA is called as the armature reaction reactance. So these are the things that you always have to remember. E1 is called as the air gap voltage, E1 is called as the air gap voltage, and EF is called as the induced voltage, and XL is called as the leakage reactance, and XA is called as the armature reaction reactance. The summation of the leakage reactance and the armature reaction reactance is called as the synchronous reactance. This is a very important point. So always XS is always equal to XA plus XL. So now we are going to draw the phasor diagram, and then we will see what is going to happen. So I am going to take this is a, we can say this is a let me take this is the reference voltage, which is the load voltage V. The current is going to lag it, so therefore the current is going to lag the terminal voltage, or we can say the terminal phase voltage. It is going to lag, the current IA is going to lag, because we are going to come to lagging load. So theta is called as a power factor angle. So theta is the angle between the load voltage and the load current. So therefore V and IA. So theta is called as a power factor angle. So now I am going to overall draw the equation IA into RA. So IA into RA is again phased with the IA. So again IA into XA. So IA into XA is nothing but say IA into XL. This is perpendicular, because in an inductor the current is going to lag the voltage. So therefore this is the voltage drop IA into XL, and this is called as the IA into XA. So IA into XL is called as the voltage drop in the leakage reactance, and IA into XA is called as the voltage drop in the leakage reactance. So therefore IA into XL is called as the voltage drop in the leakage reactance, and IA into XA is called as the voltage drop in the armature reaction reactance. So summation of all these things is called as the voltage drop in the synchronous reactance. So if you do the addition of all these vectors, which is V IA into RA, and if you do the addition of IA into XL plus IA into XA, so this is a vector sum joining the initial point with the final point is called as the EMF induced, because EMF induced is equal to V plus IA into RA plus J into IA into XA plus XL. So this is called as the EMF, which is induced per phase voltage. The per phase, always we are going to consider only the per phase values. So this is called as the EMF equation. So this is the overall induced voltage in the winding. So therefore this is called as the overall induced voltage in the stator coil per phase voltage, and this is called as the E1. E1 is the summation of the V plus IA RA plus IA into XL. This is called as the E1 is called as the air gap voltage. So this is the point that you always have to understand. So E plus IA into XA is again simply EF. So now we can say simply that if you go for the the Pythagoras theorem, this length is EF and this length is IA into XA plus XL. But if I want to know what is this length is called as this is V into cos theta and this is V into sin theta. This length is V into cos theta and this is V into sin theta. So therefore simply we can say that this is V into, this length is V into sin theta plus IA into XA plus XL is called as the XS. So therefore this is V into sin theta plus IA into XS. So this total voltage drop is nothing but which is simply equal to V into sin theta plus IA into XS. So this is called as the V into cos theta. This length is called as V into cos theta and this length is IA into RA. So by applying the Pythagoras theorem, simply we can say hypotenuse square is equal to adjacent whole square plus opposite whole square. So F square is equal to simply V into cos theta plus IA into RA whole square plus V into sin theta plus IA into XS whole square. So this is the equation we are going to get finally. So therefore F square is equal to V cos theta. So V cos theta plus IA into RA whole square plus V sin theta plus IA into XS whole square. So this is the voltage that we are going to get with the help of the Pythagoras theorem. This length is EF, this total length is V cos theta plus IA into RA, this total length is V into sin theta plus IA into XS. So therefore XS is equal to XA plus XL. XS is called as the synchronous reactance and XA is called as the armature reaction reactance and XL is called as the leakage reactance. So XS is always summation of XA plus XL. So this theta is called as the load power factor angle. Theta is called as the load power factor angle and this delta, and this delta is called as the load angle. Load angle is nothing but it is a phase angle between the EMF induced and the terminal voltage. So delta is called as the load angle. It is the angle between the EMF induced and also the terminal voltage. So delta is called as the load angle. It is a basically simply we can say it is the phase angle between the EMF induced and the terminal voltage. And this overall, this psi is called as it is the angle between the EMF induced and the input current IA, or simply we can call it as the internal power factor angle. So psi is called as the internal power factor angle, and theta is called as the load power factor angle, and delta is called as the load angle. So this is a very important point. This psi is called as the internal power factor angle, and theta is called as the load power factor angle, and the delta is called as the load angle. These are the very important points you need to always keep mind regarding these concepts. So the phase angle between the load voltage and the load current is called as the power factor angle, which is a theta, and similarly the phase angle between the EMF induced and the terminal voltage is called as the delta, which is called as the load angle, and the phase angle between the internal voltage and the internal current, which is EF and IA, it is called as the internal power factor angle. So therefore this is psi. So you can see clearly this is the theta, this is delta, and this is psi. So psi is nothing but the phi, or phi is called as the summation of the delta plus theta. You can see clearly from this diagram. So phi is equal to delta plus theta, where phi is called as the internal power factor angle, and delta is called as the load angle, and theta is called as the load power factor angle. So theta is called as the load power factor angle, and phi is called as the internal power factor angle, and delta is called as the load angle. So these are the important points that you always have to remember. So EF square is equal to V cos theta plus IA into RA whole square plus V sin theta plus IA into XS whole square. V is called as a phase voltage. Always we are going to consider only the phase voltage. V is called as the terminal phase voltage. Basically V is called as the terminal phase voltage, and IA is called as the phase current, or we can say armature current or the phase current, or simply we can call it as the phase current or the armature current. And the RA and XS all are the phase values. RA and XS are all the phase values. RA is the armature reactance, XS is called as synchronous reactance. All these are the per phase values. So V is called as the terminal phase voltage, and IA is called as the per phase current or the armature per phase current, and RA and XS all are in the per phase values. So note one important point, always in questions, the given voltage is the line voltage. So always in the questions, whatever they are going to give you, these are all the line voltages. So but the formula which is going to consider is only the phase voltages. All these formulas are going to consider only the phase voltages. So these are called as the phase voltages, but the questions they are going to give you the line voltages. So just do the star connection, line voltage is equal to root times phase voltage. So phase voltage is equal to VL by root 3. So always you have to, these are all per phase values. So but in the question they are going to give the line voltage. So by if you divide by root 3, we are going to consider into phase voltages. So here EF is called as the internal EMF induced and V is called as the terminal voltage. V is called as the terminal voltage of the across the node. This is a very important point that you always have to understand. So suppose if we connect the leading power factor load to the alternator, then what is the phasor diagram we are going to get? Up now we have learned about the lagging load, but if we connect the leading power factor load, if it is connected to alternator, then what is the phasor diagram that we are going to get? So this is called as the terminal voltage. V is called as terminal voltage, and the current is going to lead now. So whenever the current is going to lead, because it's the leading load. So this is IA. So this is called as the IA into XA. Then IA into XS is nothing but this is it is perpendicular to the voltage in an inductor is always perpendicular to the current. Or you can say it is going to, the current in an inductor is going to lag the voltage across the inductor by 90 degree. So this is the voltage. So therefore it is going to lead the current by 90 degree. So this is the voltage across the synchronous reactance IA into XL, because XS is the summation of the XA plus XL. So this is called as the IA into XS. So V plus IA into RA plus J into IA into XL is called as the, this vector is called as the EMF which is induced. So EMF which is induced. So I have already told you the phase angle between the terminal voltage and the terminal current is called as the power factor angle. So this is the theta. Theta is called the power factor angle. And the angle between the EMF induced and the terminal voltage is called as the, it is called as the delta, or we simply it is called as the load angle. This is delta. And the power factor and the power factor angle between the internal induced voltage and the internal current is called as the internal power factor angle, which is psi. So you can see clearly from this diagram that theta is equal to psi plus delta. So theta is equal to psi plus delta in this case. So theta is equal to psi plus delta, phi plus delta. So if you see clearly, the value of the EMF induced is lesser than the terminal voltage. So you can see clearly the value of the EMF induced is lesser than the terminal voltage. But you can get in another way also, the EMF induced can be greater than terminal voltage also, because in a leading load you can get the internal EMF is equal to terminal voltage, or internal EMF is greater than terminal voltage, or internal EMF is less than the terminal voltage. All these three cases it is possible only in the leading power factor load. So therefore simply we can say that, so therefore now this is the one diagram. You can also get the another diagram. In this diagram the EF value is lesser than V value, but you may get in another way, which is EF value can be greater than V. So now you will see what is the phasor diagram if EF is greater than V. So this is the diagram I am going to get. So this is the terminal voltage and this is the terminal current, but the lagging is now somewhat lesser. So if this is a theta, then this is called as the IA into RA, and this perpendicular is called as the IA into XS. So this overall vector is called as EF. So now you can see EF is always greater than V. So therefore EF is always greater than V you are going to get in this case. Then this is the diagram that you are going to get. So now we will see what is the angles that we are going to get. So therefore the angle between the terminal voltage and the terminal current is called as the load power factor angle, which is the theta, and the angle between the EF and the induced voltage and terminal voltage is called as the delta. Delta is called as the load angle, and the phi is called as the, and this is called as psi. Psi is called as the, which is the angle between the internal induced voltage and the internal current. This is called as a psi. So now if you see the angles, you can see delta is equal to psi plus theta. So delta is equal to psi plus theta. So like this you can get. So we can say that only in the leading load EF can be less than V, or EF is equal to V, or EF is greater than V. All these three cases are possible. So this is, the previous one is EF is less than terminal voltage. Here EF is greater than the terminal voltage. So this is the things that you can easily analyze from this one. So now we are going to discuss about the important concept in the alternator is called as the regulation in the alternator. So the percentage of regulation is equal to EF minus V by V into 100. So this is the important formula in the alternator, the regulation. The percentage of regulation is equal to EF minus V by V into 100, where EF is called as the
the phase voltage which is induced in the stator coils minus the terminal voltage of the stator coil by terminal voltage into 100. Whereas in the transformer, this is E2 minus V2 by E2 here. But in the transformer, in the alternator, it is reverse, which is EF minus V by V. So you have to use the terminal voltage here. Whereas the transformer, we have to use the induced voltage here. This is the only difference. So therefore, the percentage of regulation in the alternator is EF minus V by V into 100. Where EF is called as the per phase voltage across the stator coils and V is the terminal voltage across the stator coils. I have already told you the important relation EF is equal to V plus IA into RA plus J into IA into XA plus XL. But XA plus XL is equal to XS. So therefore, if you take IA as a common, then IA into RA plus J XS is nothing but ZS. So therefore, simply we can say EF is equal to V plus IA into ZS. So EF minus V is equal to IA into ZS. So therefore, EF minus V is called as the IA into ZS, means it is a voltage drop across the internal impedance of the stator coils. So at full load, what is going to happen? If you keep a full load, then the current you are going to get a maximum value. If current is equal to maximum value, then simply here more is the voltage drop. So here more is the voltage drop. So more is the voltage drop means output we are going to get very lesser, because EF minus I into ZA is equal to V, as IA into ZS is IA is very higher. So EF minus IA into ZS will be very lesser. So output we are going to get less voltage. See, terminal voltage is very less if the current is maximum. Similarly, at no load, the current is equal to 0, then definitely the terminal voltage itself is equal to EMF induced in the stator coils. So therefore, simply we can say at full load the current is very high, so more is the voltage drop across the internal impedance, so less we are going to get across the terminal voltage. At no load, the current is equal to 0, so therefore whatever the internal voltage is equal to the terminal voltage also. So V is equal to EF. So this is a very important thing that you always need to analyze. Then what is the percentage regulation that you are going to get? EF minus V is nothing but IA into ZS. So substitute here IA into ZS by terminal voltage into 100. So this is called as a percentage regulation of an alternator is the voltage drop across the internal impedance of the alternator by the terminal voltage into 100. So the percentage of regulation is equal to the voltage drop across the internal impedance of the alternator by terminal voltage into 100. So you can see clearly, if I assume IA and V as a constant, then I can say simply that the percentage regulation of an alternator is directly proportional to synchronous impedance, where ZS is called as a synchronous impedance or the internal impedance of the stator coils. So we can say that the percentage regulation is always directly proportional to the synchronous impedance. So more is the synchronous impedance, more is the percentage regulation. So more is the regulation means more is the voltage drop across the internal impedance. So therefore output voltage you are going to get less. That is the meaning of the percentage regulation. So ZS is called as a synchronous impedance is equal to RS plus J into XS. I have already told you XS is a summation of the XA plus XL. XA is called as the armature reaction reactance and XL is called as the leakage reactance. And V is called as the rated terminal voltage given on the nameplate details. So V is called as the rated terminal voltage which is given on the nameplate details, and EF minus V is called as the change in terminal voltage. EF minus V is called as the change in terminal voltage, because at no load EF is equal to V and at full load there is a V. So therefore EF minus V is called as a change in terminal voltage, because at no load V is equal to EF. At full load the rated voltage is V. So therefore simply we can say EF minus V is called as the change in terminal voltage. So if you keep more and more load, the voltage across the load is going to get decreased. At no load, the voltage across the load is very high. If you keep more and more load, the voltage is going to decrease across the load. The amount of change of voltage from no load to full load, it is called as the EF minus V. So EF minus V is going to give you the amount of change in terminal voltage from no load to full load. This drop, how much amount of change is happening, that we can figure out with the help of this EF minus V. It's a change in terminal voltage from no load to full load. So one important formula that you always need to analyze, that percentage of regulation in the alternator is EF minus V by V into 100, where EF is called as the EMF which is induced per phase in the stator coil, and V is called as the rated terminal voltage given on the nameplate details. So therefore EF minus V is nothing but IA into ZS. So always the percentage regulation is always proportional to the synchronous impedance. So now we will discuss what is the necessary of doing the regulation of alternator. So why we need to do the regulation of alternator? Because these are some of the important points which is going to give you the necessity of finding out the regulation of the alternator. See, whenever the full load is thrown off, so if you keep a full load, then the voltage across the load is minimum. Suddenly the load is thrown off, means open circuit. Then definitely the rise in voltage must be known. With respect to rise in voltage, only insulation is provided to armature conductors. And already told you, suppose if you are going to keep a full load across the alternator, suddenly the load is thrown. Definitely if you take the load off with the open circuit, and we can say no load condition, the voltage will rise. So therefore, how much amount of voltage rise must be known. Otherwise, based on that only, you are going to provide the insulation to the armature conductors. If you don't know that, then you don't know how much amount of insulation is required. Definitely, you should know the regulation. Then only based on that, you can provide the insulation for the armature conductors. So whenever the full load is thrown off, there is a rise in voltage. You must know how much amount of rise in voltage. Then how much amount of rise voltage, if you know, based on that you can provide the insulation to the armature conductors. At full load, the voltage across the load is minimum. At no load, the voltage across the load is maximum. So whenever the full load is thrown off, rise in voltage must be known. With respect to rise in voltage, only insulation is provided to armature conductors. So AVR is called as the automatic voltage regulator. So AVR is called as the automatic voltage regulator. It is designed with respect to data of the regulation of alternator. So automatic voltage regulator are designed with respect to data of the regulation of alternator. So if you have the data of the regulation of alternator, then based on that, the automatic voltage regulator you can design. So therefore, based on the data of the regulation of alternator, you can design the automatic voltage regulator. So automatic voltage regulator are designed with respect to data of the regulation of the alternator. The short circuit condition and the stability are affected by the regulation of alternator. So steady short circuit condition, and the stability are affected by the regulation of alternator. So therefore, let me suppose case here, EF is equal to V plus IA into ZS. But what is the value of IA? IA is equal to EF minus V by ZS. If terminal voltage is equal to 0, then the amount of short circuit of the armature current is equal to EF by ZS, which is very huge value, because EF is very high, so ZS is very less, the ratio is very higher, so therefore the current is very higher. So therefore the steady short circuit condition and the stability are affected by the regulation of the alternator. If suppose the load is thrown off, or simply we can say that whenever there is a short circuit across the load, the current we are going to get is a very huge value. So therefore, the steady state short circuit condition and the stability are being affected by the regulation of the alternator. And the stability is always inversely proportional to the synchronous reactance. So more is the synchronous reactance, less is the stability. So less is the synchronous reactance, more is the stability. So this is a very important point that you always need to understand. So steady short circuit condition and the stability are the important parameters which are affected by the regulation of the alternator. So steady state short circuit condition and the stability are being affected by the regulation of the alternator. So EF is equal to V plus IA into ZS. So IA is equal to EF minus V by ZS. So whenever the terminal voltage is equal to 0, the current, which is the short circuit armature current, is very huge value. It's a very huge value, and the stability is inversely proportional to the synchronous reactance. And the stability is always inversely proportional to synchronous reactance. So we can say that, see, the steady state short circuit condition and the stability are being affected by the regulation of alternator. Successful parallel operation, regulation of alternators must be known. So if you want to do the parallel operation of the alternators, then definitely you should know the regulation of the alternators. If you do not know the regulation of alternators, then it is impossible to do the successful operation of parallel operation. So if you want a successful operation of parallel operation of the alternators, then definitely you should know the regulation of the alternators. Then only a successful operation of the parallel operation is being completed. Otherwise, it is impossible. So therefore, I recommend you to do the regulation of the alternators. Then only you can go for the parallel operation. So therefore, for successful parallel operation, regulation of the alternators must be completely known. For practical old alternator, regulation is approximately 30 to 40 percentage, and in modern alternators, regulation is nearly 60 to 70 percentage. So you can see clearly for old alternators, if you go for old alternators, the regulation is very less, which is 30 to 40 percentage, whereas in the modern alternators, the regulation is very high, which is 60 to 70 percentage. So we can see clearly from this one, for practical old alternators, the regulation is approximately very less, which is nearly 30 to 40 percentage, and in modern alternators, the regulation is very high, which is nearly 60 to 70 percentage. So for practical old alternators, the regulation is approximately 30 to 40 percentage, and in modern alternators, the regulation is nearly 60 to 70 percentage. So to limit the steady short circuit current, alternator is designed with high synchronous impedance. I already told you the short circuit current is which is EF by ZS. So if you want to limit it, then you need to have a high amount of synchronous impedance. So more is the synchronous impedance, less is the steady state short circuit current. So therefore, as ZS is very high, I have already told you the percentage of radiation is highly proportional to synchronous impedance. So therefore, the radiation is very higher. So if you want to limit the steady state short circuit current, you need to have a huge amount of synchronous impedance. Huge amount of synchronous impedance directly indicates that the percentage of regulation of the alternator is also very higher. So therefore we can say that if you want to limit the steady state short circuit condition of an alternator, you should have the huge amount of synchronous impedance. Huge amount of synchronous impedance also gives you idea about the regulation. So more is the regulation. Regulation of alternator does not influence the efficiency of alternator since armature resistance is very less. See, the regulation of alternator does not going to influence the efficiency of alternator since the armature resistance is very less. I already told you, for a synchronous impedance of an alternator, in that resistance part is very less value, so it is nearly equal to J into XS. If the resistance is very less, the efficiency and the regulation are two independent things. You don't have to compare one with the other. So both are independent of each other. So you have to see both in a different manner because both are independent of each other. So therefore we can say clearly that the armature resistance of the synchronous impedance is very less. So therefore we can say that the regulation and also the efficiency both are independent terms for an alternator. So therefore we can say clearly that the regulation of alternator does not influence the efficiency of alternator since the armature reactance is the armature resistance is very less, whereas the armature reactance is very higher value. Then percentage of regulation value, which is E2 minus V2 by E2 into 100 for transformer. I have already told this important formula, which is E2 minus V2 by E2 into 100. E2 is called as the EMF induced in the secondary winding and V2 is the terminal voltage. This is the formula for the transformer. So simply we can say I2 into Z02 by E2 into 100. This is a regulation formula for the transformer. Where Z02 is equal to R02 plus J into X0 of 2, where X0 of 2 is called as the leakage reactance with respect to secondary winding, and E2 is called as the induced voltage, which is as per the nameplate rating. So this is the formula that we are going to use for the transformer. I have already told this important formula in the transformer itself. So therefore, the percentage of regulation is equal to V2 minus E2 by E2 into 100 for the transformer, which is I2 into Z0 of 2 by E2 into 100, whereas Z0 of 2 is equal to R0 of 2 plus J into X0 of t. This is with respect to secondary winding. So X0 of 2 is called as a leakage reactance with respect to the secondary winding, and E2 is the induced voltage, which is as per the nameplate rating. So the regulation of practical transformer is very less when compared to regulation of alternator because there is no armature reaction in transformer. See, in the transformer there is nothing like armature reaction. So therefore we can say that simply the regulation of the practical transformer is very less when compared to regulation of alternator, or simply we can say that the regulation of the transformer is always lesser when compared to the regulation of alternator because in the transformer there is nothing like armature reaction concept. Armature reaction concept is only for the rotating machines but not for the static machines. So therefore, as there is no armature reaction concept for static machines, so we can say the regulation of that static machines is always lesser when compared to the regulation of the rotating machines. It's a very important concept. So therefore, the regulation of the static machines is always lesser than the regulation of the rotating machines, because there is nothing like concept of armature reaction in static machines. So finally we can say that the regulation of the practical transformer is very less when compared to regulation of alternator, because there is no armature reaction in transformer. See why it is like that, because Z naught of 2, see Z naught of 2, I have already told you, percentage of regulation is directly proportional to synchronous impedance. See, in the rotating machines, synchronous impedance is going to contain the armature reaction. So if the Z value increases, then definitely the regulation is increases. But in the transformer there is no armature reaction, so there is no term of XA. XA is going to present only in the rotating machines but not in the static machines. So as XA increases, Z value increases. As Z value increases, the regulation increases. So therefore simply we can say this XA is going to present only in the rotating machines but not in the static machines. So when XA increases, Z increases. When Z increases, the regulation increases. That is what I am trying to tell you from the starting onwards. So in the static machines there is no concept of armature reaction. So there is no like XA term, which is called as the armature reactance. So if there is no, then definitely Z is less. So therefore the regulation is also less in the transformer. So finally I can conclude that the regulation of the practical transformer is very less when compared to the regulation of alternator, because there is no concept of armature reaction in transformer or in the static machines. So now we will understand what is the condition for the minimum regulation of alternator. In a transformer we have learned about the minimum and the maximum condition. Similarly now we are going to learn what is the minimum condition and also the maximum condition also we are going to study for the alternator. So for the same concept we have learned for the transformer also, minimum regulation and the maximum regulation. So similarly same concept we are going to apply for alternator also. What is the condition for minimum regulation of alternator? So let me give you the basic formula, which is EF square is equal to under root EF square is equal to V cos theta plus IA into RA whole square plus V sin theta plus or minus IA into XS whole square. This is called as the EMF induced equation, or we can say this is the voltage equation. This concept I have already told you. But here plus is used for only the lagging load and minus is used for the leading load. So EF is nothing but under root over V cos theta plus IA RA whole square plus V sin theta plus or minus IA into XS whole square. So plus is used for the lagging load and minus is used for the leading load. Then percentage of voltage regulation, I have already told you the basic formula, which is EF minus V by D into 100. With EF is called as the per phase voltage induced and V is called as the terminal voltage. So minimum regulation is obtained only at the leading power factor, because minimum regulation means we can say that minimum regulation is only possible at the negative value. Negative value means leading load. So minimum regulation is obtained only at the leading power factor loads only. So therefore EF is equal to under root over V cos theta plus IA into RA whole square plus V sin theta minus IA into XS whole square. So if I take the square on the both sides, and if I do the A plus B whole square and A minus B whole square, finally I am going to get an equation in this format, which is EF square is equal to V square cos square theta plus I square RA square plus 2V IA RA cos theta plus V square sin theta square plus IA square XS square minus 2V IA XS sin theta. If you do the expansion of the A plus B whole square and A minus B whole square. So if you do the simplification, if you take cos V square as a common, we are going to get cos square plus theta plus sin square is equal to 1. So like that we can say Zs is equal to RA plus J into XS. So if you draw the impedance diagram, this is called as RA and this is XS. Let me assume this theta S is called as the impedance angle of the, or we can say synchronous impedance angle or integral impedance angle. So therefore this is called the synchronous impedance angle. So theta S and this is Zs. So RA is equal to Zs into cos theta S and XS is equal to Zs into cos, or we can say RA is nothing but Zs into cos theta S. This is basically cos theta, or simply we can also call it as the sin theta. So this is called as the cos theta. Here this is actually theta S. This is basically theta S, not theta. This is actually theta S, because it is a theta means is the power factor of the load. It is a power factor angle of the load. Theta means the power factor angle of the load. Here we have to use the theta S. So therefore RA is equal to Zs into cos theta S, and here XS is equal to Zs into sin theta S. Here it should be S but not theta. Clearly this is not theta, this is theta S. So Ra is equal to Zs into cos theta s and Xs is equal to Zs into sin theta s. The theta s is called as the impedance angle, or we can say impedance angle. So therefore this is the theta is called as the impedance angle. Then Zs whole square is equal to Ra square plus Xs square. So mod of Zs whole square is equal to, because mod of Zs is equal to under root over R square plus Xs square. So mod of Z of S whole square is equal to R square plus Xs square. So now for this simplification of this equation, finally I am going to get EF square minus V square is equal to Ia into mod Zs into Ia into mod Zs plus 2V into cos of theta plus theta s. Here theta is called as the load power factor angle and theta is called as the impedance angle. So theta is called as the load power factor angle and theta is called as the impedance angle. So minimum regulation means the regulation should be equal to 0. So this is possible only when EF is equal to V, because voltage regulation is minimum means it should be 0. Only the same concept for transformer also, minimum voltage regulation is equal to 0. Same concept here also. Then EF should be always equal to V. So therefore if you substitute EF is equal to V, this value is going to become 0. So therefore 0 is equal to Ia into mod Zs into Ia into mod Zs plus 2V into cos of theta plus theta s is equal to 0. So therefore you are going to get finally Ia into mod Zs plus 2V cos of theta plus theta s is equal to 0. Then if you do simplification further, we are going to get, so further you are going to get cos of theta plus theta s is equal to minus Ia into mod Zs by 2 into V. See, V is called the terminal voltage, Ia is called as the armature current, mod of Zs. This is very important point. This is mod of Zs. Mod of Zs means under root over Ra square plus Xs square. So mod of Zs means under root over Ra square plus Xs square. So therefore it is a condition for the minimum voltage regulation. So this is the condition for the minimum voltage regulation. So cos of theta plus theta is equal to minus Ia into mod Zs by 2 into V, where V is called terminal voltage and mod of Zs is called as the, we can say, impedance angle. So see, it is called as the impedance magnitude value and Ia is armature current, so minus here. See, but 2 into V is always greater than the Ia into mod Zs. 2 into V is always, we can say, denominator is always greater than the numerator. So approximately this ratio is nearly equal to 0. So therefore approximate condition is cos of theta plus theta is nearly equal to 0. But this is the exact condition. For the minimum regulation, voltage regulation. But if you want the approximate condition, the denominator is always higher than the numerator. So this ratio is nearly equal to 0. So therefore cos of theta plus theta is nearly equal to 0 means cos 90. So theta plus theta is nearly equal to 90 means theta is equal to 90 minus theta s. So theta is nothing but tan inverse of Xs by Ra. You can get from the impedance angle. So theta s is nearly equal to. So theta is nearly equal. I've already told you Xs is very huge value when compared to Ra. So theta s is nearly equal to 85 degree. Then what is the theta? If you substitute 85, we are going to get 90 minus 85 is nearly equal to 5 degree. So therefore, whenever the load power factor angle, so what is the cos theta? Cos theta is nearly equal to huge value. It is nearly equal to 1, but not exactly. So therefore, we can say that near to unity power factor, in the leading region, nearly equal to unity power factor, we are going to get the minimum voltage regulation. Same concept for the transformer also. There also, the leading power factor, whenever it is nearly equal to unity, there you are going to get the minimum voltage regulation. So therefore, this is the huge principle that you always have to understand. So minimum regulation is obtained nearly at the unity power factor angle in the leading region. So theta is called as the leading power factor angle of the load, and theta is called as the impedance angle of the Zs, and the Zs is equal to Rs plus Jxs. It is basically, Zs is nothing but it is Ra. This is actually Ra, not Rs. This is the Ra plus Jxs. So you can see clearly Zs is equal to Ra plus Jxs, and Ra is always lesser than the Xs. So Rs is always lesser than the Xs. So because of this only we are going to get nearly equal to 85 degree. Then what is mod s? Mod of Zs is equal to under root over Ra square plus Xs square. The mod of Zs is equal to under root over Ra square plus Xs square. So we can say that minimum regulation, so minimum regulation is obtained nearly at the unity power factor angle, and we can say that simply same concept is also applied for the transformer also. So if you want the exact expression, which is cos of theta plus theta is equal to minus Ia into mod Zs by 2 into V, where V is called as the terminal phase voltage. So for alternator, minimum regulation is obtained at leading power factor and it is very near to unity power factor load. So for alternator, minimum regulation is obtained at the leading power factor load and it is very nearly equal to the unity power factor load. So therefore we can say that for alternator, minimum voltage regulation is obtained at the leading power factor load and its power factor is very near to unity power factor load. So similarly we can say that for alternator, minimum voltage regulation is obtained at leading power factor load and its power factor is very near to the unity power factor load. So this is a very important point that you always need to understand. But if you want the exact expression, which is cos of theta plus theta is equal to minus Ia into mod of Zs by 2 into V. So now you will understand the another condition, which is for the condition for the maximum regulation of alternator. So in the previous one we have learned about the minimum regulation. The condition is cos of theta plus theta is equal to minus Ia into mod of Zs by 2 into terminal voltage. But for maximum regulation of alternator, same concept we have studied in the transformer. The maximum regulation is going to occur for a transformer at the lagging load. Same concept we are going to apply here also. It is obtained at the lagging power factor load. It is obtained at the lagging power factor load. So therefore we can say simply it is going to obtain at the lagging power factor load, and I want to know what is the expression of this one. I have already told you for lagging load we have to use the symbol plus. So F square is equal to V cos theta plus Ia into Ra whole square plus V sin theta plus Ia into Xs whole square. Then after doing the expansion of A plus B whole square and A plus B whole square here, finally we are going to get Ef square minus V square is equal to Ia square into Zs plus 2V into Ia into Zs into cos of theta minus theta s. Here Zs is nothing but it is mod of Zs. Actually it is mod of Zs. It is basically mod of Zs. It's not like just Zs. It is nothing but magnitude. Here basically it is a mod of Zs. This is basically mod of Zs. Ef square minus V square is equal to, which is simply we can write, which is Ia square into Zs square plus 2V into Ia into Zs into cos of theta minus theta s. This is for the first equation 1. Here Zs is nothing but mod of Zs. So this is a very important point that we have to use the magnitude. Mod of Zs means under root over Ra square plus Xs square. So now I am going to differentiate the equation 1 with respect to theta and equal it to 0, because if I am going to differentiate this above equation with respect to theta and if I equate to 0, finally we can say that all these things are constant values. So if I equate to 0, then definitely I am going to get, which is sine of theta minus theta is equal to 0, then definitely theta is equal to theta I am going to get. So if I do the differentiation of this above equation with respect to theta and if I equate to 0, I am going to get sine of theta minus theta is equal to 0, then definitely sine is 0 only when sine of 0. So therefore theta minus theta is equal to 0. So then theta is equal to theta s. So whenever the load angle, the lagging load angle, the power factor of the load is equal to theta s by internal impedance angle, then only we can say it is said to be, at this condition only we are going to get the maximum regulation of the alternator. I have already told you theta is it's very huge value. It is nearly equal to 85 degree. So theta is also nearly equal to 85 degree. Then what is the cos theta? As the theta increases, the cos of function will decreases. So therefore it is nearly equal to 0 power factor, 0 lagging power factor. So therefore for the alternator, maximum regulation is obtained at the lagging power factor and it is very near to the 0 power factor lagging. So we can say that simply for the alternator, maximum regulation is obtained at the lagging power factor load and its power factor is very nearly equal to 0 power factor lagging. Whereas for the minimum regulation, for the alternator, minimum regulation is obtained at the leading region and its power factor is nearly equal to the unity power factor. Similarly, for the alternator, maximum regulation is obtained at the lagging power factor region and its power factor is very nearly equal to the 0 power factor lagging. So these two concepts now we are going to combine together and we are going to draw the overall voltage regulation graph of the alternator. So for minimum voltage regulation, the condition is cos of theta plus theta is equal to minus Ia into mod of Zs by 2 into terminal voltage. Whereas here for the maximum voltage regulation, the lower power factor angle is equal to internal impedance angle, which is theta s. Based on the two concepts that we have learned, we are going to draw the overall voltage regulation of the alternator. So regulation diagram of the alternator for all the conditions we are going to consider. So this is the lagging power factor region and this is the leading power factor region. The first thing we have learned about the leading power factor region, in the leading power factor region I have already told you EF can be greater than V, EF can be less than V, EF can be equal to V. So whenever EF is equal to V, we are going to get zero voltage regulation. Whenever EF is greater than V, we are going to get positive voltage regulation. Whenever the EF is less than V, we are going to get a negative voltage regulation. All this is possible only in the leading load. But in the lagging load, always EF is always greater than V, irrespective of the power factor angle. So that is the reason voltage regulation is always positive in the lagging load, but it is a positive, it is a negative, and it is zero only in the leading power factor. And I have already told you that zero, or you can say minimum voltage regulation, is possible in the leading power factor, and its power factor is nearly equal to unity. You can see its power factor is very near to unity. This is 0, this is 0.2, this is 0.4, this is 0.6, this is 0.8, and this is 1. So you can see its power factor is very near to unity. Whereas in the lagging power factor, the voltage regulation you can see it is, we are going to get the maximum voltage regulation at a power factor which is nearly equal to 0 power factor. So therefore this you can see clearly the power factor of the lagging load at the maximum is very nearly equal to 0. So this is 1, means this is 0.8, 0.6, 0.4, 0.2, this is 0.8, 0.6, 0.4, 0.2 and 0. So you can see clearly this middle one is called as a unity power factor. Here 0.8, 0.6, 0.4, 0.2, here also 0.8, 0.6, 0.4, 0.2 and 0. So at the unity power factor always you are going to get a positive voltage regulation. So at the unity power factor always you are going to get a positive voltage regulation. So AB, so let me assume this point is A, this line is AB. So AB is called as a regulation at the unity power factor load, and this C is called as a power factor at the zero regulation. So C is called as the power factor at zero regulation. So you can say C is called as a power factor of the leading load at zero regulation, and it is said to be a minimum regulation. It is said to be a minimum regulation because its value is equal to 0. So therefore we can say its value is equal to 0. And I have already told you the condition cos of theta plus theta s is equal to minus Ia into mod of Zs by 2 into terminal voltage. All these concepts I have told. So therefore now you can see clearly this is the graph you are going to get. This graph is independent of the prime mover speed, irrespective of the prime mover speed. So irrespective of the prime mover speed, this graph is always same. Irrespective of the prime mover speed, this is the constant graph you are going to get. So this graph is independent of the prime mover speed. So now let me understand one important point. Suppose at 0.8 lagging power factor, let me assume x1 is the voltage regulation, and at 0.8 leading power factor, the voltage regulation is x2. So from this graph we can see clearly x1 is always greater than x2. The magnitude part, only I am going to take the magnitude part. See, this graph is very higher here, but it is very lower here. So therefore we can say that at 0.8 power factor lagging, let me assume x1 is the voltage regulation, and at 0.8 power factor leading, x2 is the voltage regulation. Let me consider only the magnitude part. The magnitude part of the x1 is always greater than the magnitude part of the x2. So this is a very important point that you always have to understand. So just by seeing the graph only, we can say that this part is very higher and this part is very lower. This is the leading region and this is the lagging region. This is the unity. This is 0.8, 0.6, 0.4, 0.2. As you go far from it, the power factor decreases. Similarly, if you go far from origin, its power factor will decrease. At origin, the power factor is unity. So finally, I can conclude that this is a voltage regulation graph of a alternator. Same graph we are going to get for the transformer also. All these things I have already told in the transformer class. So we can see clearly that for a leading load, whenever the power factor of the leading load, if it is nearly equal to unity, there we are going to get the minimum voltage regulation is equal to 0. Whereas if you want to get the maximum voltage regulation, you need to go for the lagging load, and its power factor of the load is nearly equal to the 0 power factor lagging. So these are the concepts that I have already told you. So this graph is independent of the prime mover speed. No matter whatever the speed of the prime mover, this is a constant graph we are going to get. So this is the beautiness of the graph of the regulation diagram of an alternator. So same graph we are going to obtain for even the transformer also. This is called as the positive voltage regulation, and this is called as the negative voltage regulation. And one is called as the unity power factor load. So let me discuss the another concept which is called as the characteristics of the alternators. So now we are going to draw different characteristics of the alternators. So different characteristics by conducting the different tests tests on the alternators. So by connecting the different tests on the alternators, we are going to get different characteristics of alternators, which are called as the first one is called as the open circuit characteristics. Open circuit characteristics means it is a graph between the E0 and IF. IF is called as the field current and E0 is called as the no load per phase voltage. No load per phase voltage in the stator coil. So if you draw the graph between the no load per phase voltage and the field current at a constant rotor speed, then it is called as the open circuit characteristics. So open circuit characteristics means it is the graph between the no load EMF induced in the stator coil per phase with respect to field current at a constant rotor speed. Then short circuit characteristics means it is a graph between the armature current and the field current at a constant rotor speed. So the short circuit conventions means if you draw a graph between the armature current and the field current at a constant rotor speed, it is said to be a short circuit characteristics. Short circuit characteristics means it is the graph between the armature current and the field current at the rotor speed as constant. Then zero power factor characteristics. Zero power factor characteristics means it is a graph between the terminal phase voltage with respect to the field current. With respect to the field current, and the conditions are the power factor of the load is a constant and the rated current we are going to get a armature current. We should use a constant rated current and the speed of the rotor is also constant. So these are the conditions that must be met before doing this test. And the load characteristics means it is a graph between the terminal voltage with respect to field current, but here the power factor is a constant of the load and the IA is also constant rated current and the speed is also constant. Then external characteristics. External characteristics means it is a graph between the terminal voltage and the armature current at the power factor as a constant, at the field current as constant, and the speed of the rotor is also constant. Finally, the compound characteristics means it is a graph between the field current and the armature current whenever the power factor is a constant, terminal voltage is a constant, and the speed of the rotor is constant. So these are the different characteristics that we are going to draw with these conditions. So let me repeat this concept again so you can understand in a very easier format. So let me repeat this concept again. The characteristics of the alternators. The characteristics of the alternators. See, open circuit characteristics. So open circuit characteristics means it is a graph between the EMF induced at no load. So let me draw the characteristics of the alternators. The different tests we are going to see, it is called as the open circuit characteristics means if you draw the graph between the EMF induced per phase at no load with respect to field current at a constant speed of the rotor is called as the open circuit characteristics. And similarly, short circuit characteristics means it is a graph between the armature current and the field current whenever the rotor speed is constant. Similarly, ZTF characteristics means we have to draw the graph between the terminal voltage and the field current at this condition, which are the power factor of the load is a constant and the IA is equal to, see, power factor means we have to use the zero power factor. See, the pure lagging load we need to consider, and also IA is equal to constant rated and speed is equal to constant. So these are the conditions. At these conditions we have to draw the graph between the terminal voltage and the field current. Same for load characteristics. For load characteristics also same thing, which is we have to draw the graph between the terminal voltage and the field current at the power factor is a constant and IA is also constant, which is rated, and the speed of the rotor is also constant. The next one was the external characteristics. It is a graph between the terminal voltage and the terminal current, which is IA, at the power factor as the load constant and IF is also constant and the speed of the rotor is constant. And the compound characteristics means it is a graph between the field current and the armature current at the power factor as a constant, terminal voltage is a constant, and the speed of the rotor is also constant. All these graphs we are going to study one after the other in a very detailed manner with very deep analysis. And now we will discuss one new concept which is called as the characteristics of the alternators. So we are going to perform different tests on the alternators to figure each and every aspect of the parameters of the alternator. So the different types of tests are there. The first one is called as the open circuit characteristics. Open circuit characteristics means we have to find what is the graph between the no load induced voltage, or you can say no load induced voltage in the per phase of the stator coils versus the field current whenever the rotor speed is constant. So we have to maintain this condition as a constant. So based on this we have to draw the graph between these two parameters. Similarly, short circuit characteristics means it is a graph between the armature current versus the field current whenever the speed of the rotor is a constant. You have to maintain this one as a constant. Similarly, ZPF characteristics means zero power factor characteristics means it is a graph between the terminal voltage versus the field. It is a graph between the terminal voltage versus the field current at these are the conditions you must always consider, which is power factor is equal to constant and the armature current is equal to constant and it should be a rated current and the speed of the rotor should be always constant. Similarly, load characteristics. Load characteristics is also same thing, which is the graph between the voltage versus the field current and the power factor was the constant and the armature current was constant and it must be rated 1 and the speed is equal to constant. Now we will discuss the external characteristics. It is the graph between the terminal voltage versus the armature current. Whenever the power factor of the load is a constant and the field current was the constant and the motor speed is also constant. Compound characteristics means it is the graph between the field current versus the armature current and the power factor is equal to constant, the terminal voltage is equal to constant and the speed of the rotor is equal to constant. So these are the different types of tests that we are going to conduct on the alternator. So we are going to see each one in a very detailed manner. So one after the other we are going to see each and every aspect. First test that we are going to perform on the alternator is the open circuit characteristics. That you can see clearly here is the open circuit characteristics of the alternator. It is a graph between the E0, or you can say it is called as the per phase induced voltage versus the field current at the rotor speed is constant. So we'll take this one as a prime mover. So this is a prime mover. We are going to rotate this prime mover. So whenever we are going to rotate this prime mover at a constant speed, on the prime mover we are going to keep this one. On the prime mover we are going to keep this field winding. So field winding we are going to give DC supply. So this is the DC supply that we are going to give a variable DC supply to the, we can say, field current or we can say field winding. Then what is going to happen? We have to maintain the rated, or you can say the primary speed as a constant, and this is the armature. Armature is basically placed on the stator. So therefore here we are going to open circuit means we have to open circuit these three terminals. So these three terminals we need to open circuit, and then we have to keep a voltmeter across the line and the neutral. It is called as a per phase voltage. So same thing, it is called as a per phase voltage of the induced voltage at a no load condition. Means we have to open circuit all these lines. That's what is called as a open circuit characteristics of alternator. So based on this we have to draw the graph between this induced voltage and the field current if we vary this one. So speed is equal to rated speed. I have already told you it's a rated speed that we need to maintain for the prime mover. It must be always constant. So then we will see what is going to happen. As I have already told you this important formula, which is the EMF which is induced, the RMS value of the EMF which is induced per phase is equal to 4.44 into phi ft into kW. Phi ft into kW, where kW is called as a winding factor, P is called turns per phase, F is called as supply frequency, and phi is called as the average flux. Here phi indicates in reading machines, phi indicates it is a average flux, whereas in electrical machines that indicates the maximum flux. So therefore you can see the flux is always directly proportional to field current. If the field current increases, flux increases. So if field current increases, flux increases, and the flux is directly proportional to E. So therefore simply we can say whenever the field current increases, flux increases. As flux increases, E increases. So therefore E is directly proportional to phi and phi is directly proportional to IF. So therefore whenever IF increases, flux increases. So whenever flux increases, then also the induced voltage, the RMS value of the induced voltage per phase is also going to increase. So now if we draw the graph between the field current and the induced voltage per phase, the RMS value of the induced voltage per phase, if we draw this diagram, we are going to get like this, like a parabola. You can see somewhat like a parabola you are going to get. So let me assume these are the 3 points, point A, point B and point C. So this point B is called as a knee point, means after this there will be a saturation effect is going to occur, but before that there will be no saturation effect. So after B there will be saturation effect, and before B there will be no saturation, means unsaturation region. So therefore you need more amount of flux to increase the EMF here. You need more amount of field current to increase the EMF in this region because of saturation effect, because IF, whenever IF increases, the fluxes become saturated, so the amount of change in E is very less in the saturation region. So therefore let me assume this is a rated voltage. So this is the rated per phase voltage I am going to get at a certain current, and this is called as a 1.5 1.25 times the rated voltage that we are going to get. Let me assume this is a point C. So AB is called as the unsaturation region and BC is called as the saturation region and VR is called as the rated terminal voltage, or we can say rated voltage, per phase voltage. So rated per phase voltage, this is VR. VR is called as the rated per phase voltage. So now you will see what is the consequences which are going to occur. In OCC, open circuit characteristics, the alternator is operated at the rated speed, which is n is equal to constant. Means the primer should be always measured at a constant speed and it should be a rated one. So to obtain the open circuit characteristics of alternator, then alternator is operated at the rated speed, which is n is equal to constant for the prime mover. It is also called as the no load characteristics or magnetization characteristics. See, this OCC, this open circuit characteristic, is also called as a no load characteristics because we are not keeping any load, and it is also called as a magnetization characteristics. And in this, no armature reaction is included. Why there is no armature reaction? Because there is an open circuit in the armature coil. So whenever there is an open circuit armature coil, the armature current is equal to 0. So if IA is there, the armature current is present, then only the armature flux is going to present, then only there will be distortion effect of the overall flux. It is called the armature reaction. As it is open circuit, armature current itself is equal to 0. So therefore the armature flux is equal to 0. So therefore there is no armature reaction. So there is no armature reaction is included in this open circuit test. It is designed to get the rated voltage above the knee point. See, we try to always get the rated phase voltage after the knee point. We always try to design to get the rated voltage after the knee point, or simply we can say in the saturation region we try to get the rated RMS phase voltage. So these are some of the important points that you should always be careful while conducting the open circuit test on the alternator. So to obtain the OCC, alternator should be operated at the rated speed and it should be a constant one. It is also called as the no load characteristics or the magnetization characteristics, and in this no armature reaction is included. It is designed to get the rated voltage above the knee point. All about this. This is all about the OCC. So we can say clearly the graph between the RMS value of the phase voltage, induced phase voltage versus the field current. So you are going to get in this graph. So this is called as the open circuit characteristics. So therefore we have successfully performed the open circuit test on this alternator. And now we will perform another test which is called as the short circuit characteristics of alternator. So we try to figure out the short circuit characteristics of the alternator. See, short circuit characteristics means I have already told you we have to draw the graph between the armature current versus the field current at the rotor speed is constant. So this is a graph that we need to perform, we need to get, which is the graph between the armature current versus the field current whenever the speed of the rotor is a constant. So this is a prime mover. I am going to rotate the prime mover at a constant speed, at a constant rated speed. And this is the, we can say this is called as a field winding. So field winding is basically kept on the prime mover. So therefore we are going to give a variable basis applied to this field winding. And this is called as the armature coil which is present on the stator. I am going to connect in a star connected fashion, and then short circuit means I need to do the short circuit. So I need to do the short circuit across these three terminals. Across these three terminals I need to do the short circuit. And let me assume I want to find what is the value of the current. So here I am going to use an ammeter to figure out the armature current, per phase armature current. And we is called as the per phase RMS value of the per phase induced voltage. So therefore this voltmeter is going to give you the per phase induced voltage, and this the ammeter is going to measure the armature current. So now here we have to make the rotor speed is a constant one and it should be a rated one. I have already told you this coil is going to have some impedance. I have already told you this coil is going to have some impedance which is called as the RA plus JXS. I have already told you the resistance is very less when compared to XS. So we can nearly approximate it to J into XS. So if you draw the graph between the armature current and the field current. So if you draw the graph between the armature current and the field current. So if you draw the graph between the armature current and the field current, you are going to get a straight line which is passing through origin. So if you draw a graph between the armature current and the field current, you are going to get a straight line passing through origin for all the time. So you can see clearly, if you draw the graph between the armature current and the field current, So whenever you increase the DC supply voltage for of the field winding, the IF increases. So whenever IF increases, the flux increases. So whenever the flux increases, the armature current is also increases. So therefore, we are going to get a straight line which is passing through origin for all the time. Suppose, let me take a small point here. For IF1, the armature current is IA1. So like that we can say the slope is almost constant. So during short circuit test, nature of power factor is lagging because we can say that if you go for the short circuit test, the synchronous impedance is only purely reactive, so we can say power factor is lagging in nature. So therefore, it is very near to the zero power factor lagging, but not exactly because we have approximated it. So it is nearly equal to zero power factor lagging. And the nature of armature reaction is degradation. I've already told this important point. In a synchronous generator or alternator, whenever there is a pure lagging load, we can say that the IA is going to lag EF by 90 degree. So phi A and the phi F are quite opposite of each other. So there will be demagnetization effect is going to occur. So therefore the nature of the armature reaction is demagnetization. In a short circuit test, what is the resultant air gap flux, which is phi F minus phi A, because phi A is quite opposite to the phi F. So whenever the IF increases, flux increases, so IA increases. As IA increases, phi A increases. As phi A increases, overall resultant air gap flux will decrease. So alternator is operated in the unsaturation region, whereby SSC is a linear one. So therefore we can see, so the resultant air gap flux is going to get decreased. Whenever the resultant air gap flux decreases, we can say that the EMF, we can say that simply we are going to get a linear characteristics. So we are going to always get we are going to operate in the unsaturated region, or simply we can say we are going to operate in the unsaturated region for all the time. So therefore the short circuit characteristics are always linear in shape. So whenever, because of this demagnetization only, the resultant air gap flux is going to decrease. So we always operate in the unsaturation region. So if you draw the graph between this I and IF, you are going to get a pure linear characteristics passing through origin for all the time. So therefore, in the short circuit test, the resultant air gap flux decreases. So therefore, the armature is going to operate in the unsaturation region. So thereby, short circuit characteristics are linear in nature. So in the short circuit test, by knowing experimental data of one field current and corresponding armature current, complete SSC can be obtained because SSC is linear. See, if you know at least one point, for a particular value of IF1, if you know the particular value of IF1, then just make it point. So just take that point and draw a straight line from origin to that point, and you can extend it. So therefore you are going to get the complete characteristics of the SSC. So if you know at least one point, then you can get the complete characteristics of that SSC, because it is a straight line passing through origin for all the time. So therefore if you know any one point, then just draw a straight line from origin to that point and extend it. So you are going to get the complete characteristics of this SSC. So in the short circuit test, by knowing the experimental data of one field current and corresponding armature current, then complete SSC can be obtained because SSC is linear in nature. So this is one of the important points that you need to always understand. So therefore, this is the complete analysis of the short circuit characteristics of alternator. So therefore, during short circuit test, the nature of the power factor is lagging, and it is near to the zero power factor lagging, and the nature of the armature reaction is demagnetization. In the short circuit test, the resultant air gap flux decreases. So alternator is going to operate in the unsaturation region, thereby short circuit characteristics is linear in nature. So in the short circuit test, by knowing the experimental data of one field current and corresponding armature current, complete SSC can be obtained because SSC is linear shape. Now we will understand one more important concept, which is called as the zero power factor characteristics. The third test was the zero power factor characteristics. Means I have already told you, here we have to draw the graph between the terminal voltage versus the field current. At the power factor of the load is a constant, and the armature current is a constant with rated 1, and the speed of the rotor is a constant. So these are the conditions. So now we will see how to draw this, how to make this switch. I have already told you, here we have to keep the prime mover. On the prime mover, we are going to keep this field winding. And I have already told you, we have to always rotate with a constant speed, and it is basically a rated 1. And this is the DC supply. So we are going to give variable DC supply because we need to change the field current. And here it is a star connected armature coil present on the stator. So this voltmeter is going to measure the per phase voltage, and this is the ammeter is going to measure the armature current. So here now we have to keep a load which is purely inductive load. See, purely inductive load we need to keep because it is a zero power factor characteristics, means the load should be purely inductive load. So therefore the power factor of the load is nothing but 0 because it is a purely inductive load. So it's a three-phase inductive load. So therefore now if you want to express in terms of per phase, which is EF is equal to terminal voltage plus IA into ZS. So terminal voltage is equal to EF minus IA into ZS. So therefore V is called as per phase terminal voltage is equal to EF minus IA into ZS. So we have to draw the graph between the terminal voltage, the terminal per phase voltage and the field current. So now listen carefully. This is the terminal voltage and this is the field current. This is the graph that we need to perform. I have already told you one important point here. V is nothing but EF minus IA into ZS. So first we will draw what is the OCC characteristics. OCC means simply I can say, so OCC means I have already told you one important point regarding the OCC. It is a graph between the EMF, the no load per phase voltage with respect to the field current. So this is the OCC that we are going to get. This graph I have already drawn in the first section itself. So therefore this is the graph between the per phase, the RMS value of the per phase EMF induced at no load with respect to field current IF. So this is the graph that we are going to get OCC with respect to IF. But this is called as EF minus IA into ZS. So we need to go further inside. So therefore further inside we have to go, which is IA into ZS. It is nearly equal to IA into XS because I have already told ZS is nearly equal to XS. So you have to come downward by a small amount of which is called as the IA into ZS is nearly equal to IA into XS. So if you draw like this, if you draw with the same shape but with a smaller amount of depth wise, this is called as a zero power factor characteristics. Only this portion we can draw practically but not the everything. So only the small amount of portion we can draw practically but not the everything. So this is called as a OCC. OCC minus IA into ZS, it is nearly equal to IA into XS. So further deep inside, this is called as the graph between the terminal per phase voltage with respect to field current. Only this amount of graph you can draw practically. And how to get this point A? So how to get this point A? We will see how to figure out this point A, which is if you extend it, it is going to meet certain point A. So what is that point we need to figure out? Here always we have to keep the armature current as rated condition. I have already told you the conditions for drawing this zero power factor characteristics are the power factor of the load should be constant and it should be purely inductive in nature, and the IA is nothing but it is a constant and it should be a rated one, and the speed of the rotor should be always constant. So these are the conditions that we need to maintain to draw this graph. So if IA is a constant, XS is also constant, so therefore the amount of depthness is constant for each and every point. So at each and every point, if you go inward by small amount of IA into XS is a constant for each and every point. So if you make that one and if you draw, you are going to get a graph like this because IA is a constant, X is a constant, its overall value is a constant. So therefore just you have to go further deep by a small amount of this much amount of value, and if you draw this one, it is called as a zero power factor characteristics. And if you want to know how to get this point here, then we will get only this by the short circuit characteristics. I have already told you with the help of OCC we have got these characteristics, but if you want to know the point A, then we have to take the help of the short circuit characteristics to get this point A. So the short circuit characteristics is a graph between the IA and the IF. So therefore you can see clearly whenever IA is rated, so whenever the IA is rated, so for that amount of field current, for this amount of field current, you should maintain the IA as a constant. See, even at this point A also, the armature current is a constant and it is a rated one. So if you get this one IA rated, so at IA rated is going to get at a certain value of field current. Let me assume this is the A. So same A you are going to take here also. So therefore, listen carefully. At this field current, which is point A, here also the current is a constant and it is a rated one. The armature current is a constant. So we have to see on this y-axis at what point we are going to get the rated value of the armature current, and at that particular point you have to take that field current. So that field current is called as the point A. So we have to draw this point A here also. So therefore simply we can say that we can know this point A, but we only know only this portion of this graph. So we have to extend up to this point A like a pictorially. So therefore, this is the overall characteristics of the ZPF. Which you see clearly, we have taken the help of the OCC and also this SCC. So to draw the ZPFC, we have taken the help of the OCC and also the SSC. So we have taken SSC to help SSC characteristics help to figure out the value of the point A. See, at this amount of field current, we are going to get the rated armature current. And we have taken the OCC help to draw the characteristics of this one, because this terminal voltage is lesser than the field, the no load EMF induced by a small amount of, this is called as the degrade, or we can say this much amount of less we need to take. So therefore, just from downward, this is a constant value. So if you draw all these points, we are going to get like this. So only this portion we can draw, and we have taken this one with the help of, and we have drawn this graph with the help of this OCC, and we have known this point here with the help of the SCC. So this is a very important point that you always need to keep remember. So if you extend this point, so this amount of field current and this amount of field current is always same. So these are some of the important points regarding this ZPFC characteristics. To obtain the ZPFC characteristics, the alternator can be connected to either three-phase inductive load or under-excited synchronous motor, because under-excited synchronous motor is going to act like a inductive load, whereas the over-excited synchronous motor is going to act like a reactive load. This is the capacitive load. Sorry. Therefore, this is a very important point that you always need to understand. So therefore, under-excited synchronous motor is going to act like a inductive load, three-phase inductive load, whereas the over-excited synchronous motor is going to act like a three-phase capacitive load. So to obtain the ZPFC characteristics, we need to connect a purely inductive load. So a purely three-phase inductive load, we need to connect either we can connect the three-phase inductive load or we can connect the under-excited synchronous motor, because under-excited synchronous motor is going to act like a three-phase inductive load, and I will discuss this point in the coming classes in the concept of the synchronous motor. In the ZPFC characteristics, armature reaction effect is included. Why it is included? Because there is a load. Whenever there is a load, the armature current is present. So whenever the armature current is present, definitely the armature reaction is present. So armature flux is present. So therefore the armature reaction is present. So therefore we have to include the armature reaction. So armature reaction effect is included with the help of XS. XS will have XA plus XL. XA is called as the armature reaction reactance. So therefore we are going to include the armature reaction effect also in this ZPFC characteristics. So in the ZPFC characteristics, point A is obtained from the short circuit characteristics. I've already told you, see, we are going to figure out the point A with the help of the short circuit characteristics. So OA is called as the field current required to circulate the rated armature current when the terminal voltage is equal to 0. So this is a very important point. OA is nothing but it is a field current. It is a field current required to circulate the rated armature current whenever the terminal voltage is equal to 0. So therefore, we can say that OA is called as the field current which is required to circulate the rated armature current and is a constant one whenever the terminal voltage is equal to 0. So OA is called as this much amount of field current is required to circulate the rated armature current whenever the terminal voltage is equal to 0. In the short circuit test, the output terminals of alternator is shorted. So in the short circuit test, the output terminals of alternator is shorted, but voltage reading is not equal to 0 because V is equal to IA into ZS. This point you need to understand in the concept of the short circuit test characteristics. In the short circuit test, if you see clearly, output we are going to do the short circuit, but the voltmeter is going to read which is equal to, it is going to read the per phase voltage which is IA into ZS. So the voltmeter is going to measure the voltage, it is nearly equal to IA into ZS. So therefore, in the short circuit test, the output terminals of alternator is shorted, but voltmeter is going to read not equal to 0 and the voltmeter reading is equal to IA into ZS. Because ZS is equal to RA plus JXS and RA is very very less, so we can say ZS is nearly equal to J into XS, and XS is the summation of the XA plus XL. XL is called as the leakage reactance and XA is called as the armature reaction reactance. Means we are going to include the armature reaction effect also. So OA is called as the amount of field current required to compensate the voltage drop due to leakage current and armature reaction voltage drop. So OA is called as the field current required to compensate the voltage drop due to the leakage current and the armature reaction voltage drop. So this much amount of field current is required So this much amount of field current is required to compensate the voltage drop due to leakage current reactance and the armature reaction voltage drop. So this XL and XA. So therefore, this much amount of field current is required to compensate the voltage drop due to leakage reactance and the armature reaction. So therefore, field current is required to compensate the voltage drop due to leakage reactance and the armature reaction reactance. Or simply we can say the field current required to compensate the voltage drop due to the leakage current and the armature reaction reactance. See, whenever the terminal voltage is equal to 0, then what is going to happen? Whenever the terminal voltage is equal to 0, EF is equal to IA into ZS. So therefore, EF is equal to IA into ZS. So therefore, this much amount of field current, see, EF is equal to IA into ZS. So whenever the terminal voltage is equal to 0, so therefore you need this much amount of field current is required to compensate the voltage drop due to the armature leakage reactance and the armature reaction reactance. So this is a very important point. Whatever the drop in leakage reactance and whatever the drop in the armature reaction, you need to compensate with the help of this much amount of field current. So listen carefully. This much amount of field current is required to compensate the voltage drop in the leakage reactance and the armature reaction reactance. So therefore, OA is called the field current which is required to compensate the voltage drop due to leakage current and the armature reaction voltage drop, because at this point the terminal voltage is equal to 0. So whenever the terminal voltage is equal to 0, EF is equal to IA into ZS. So therefore, there is a small amount of voltage drop across the internal impedance. So this much amount of field current is required to compensate the voltage drop in the armature reaction reactance and the leakage reactance reactance. Here I can say OA is called as a field current required to compensate the voltage drop due to leakage current and the armature reaction voltage drops. This is all about the ZPF characteristics. So up to now we have drawn the OCC, SCC and ZPFC. So now we will further move forward.